Can we be alone in the universe? Several questions have inspired humans throughout history. Many ancient Greek philosophers believed intelligent beings could be found far beyond Earth. When the first telescopes were trained on the Moon in the 17th century, some eminent astronomers interpreted lunar features as proof of an inhabited world. Only 100 years ago, belief in a civilization on Mars became so widespread that the term Martian became synonymous with alien. But despite this historical interest in the possibility of extraterrestrial life, until quite recent times, few scientists have devoted any effort to understanding the issues surrounding it, let alone to doing a serious search for life. In the past 2 decades, however, a remarkable convergence of biology, geology, astronomy, and other sciences has suddenly placed the issue of extraterrestrial life at the forefront of research. Advances in our understanding of the origin of life on Earth are helping us predict the conditions under which life might arise in other locations. Discoveries of microbes thriving under extreme conditions, at least by human standards, on Earth have raised hopes that life might survive, even in some of the harsh environments found elsewhere in our solar system. Proof that planets exist around other stars, first obtained in the 1990s, has added impetus to studying the conditions that might allow life in other star systems. Technological advances enable us to engage in unprecedented, large-scale scrutiny of the sky for signals from other civilizations, spurring heightened interest in the search for extraterrestrial intelligence, which is often abbreviated as SETI. Perhaps most importantly, scientists have found the interdisciplinary study of issues related to the search for life beyond Earth to have intrinsic value, independent of whether the search is ultimately successful. Given the intense research efforts undertaken by the scientific community and the long-standing public fascination with the search for life, it should be no surprise that the study of life in the universe, also known as astrobiology, has become one of the most publicly visible sciences. Colleges have also acknowledged the increasing significance of this discipline, and numerous institutions have started to implement astrobiology documentaries. Why search for life in the universe? The swift increase in research interest in astrobiology may not warrant the establishment of new courses for non-science majors. But the subject has at least 3 crucial features that together make a strong case for adding it to the standard science offerings. 1. The interdisciplinary nature of the study of life in the universe offers a broader understanding of the range of scientific research than a course in any single discipline. 2. The public's fascination with unidentified flying objects and alien visitation offers a unique opportunity to use life in the universe courses to teach about the nature of science and how to distinguish true science from pseudoscience. 3. The science of life in the universe considers many of the most profound questions we can ask, including, what is life? How did life start on Earth? Are we by ourselves? Could we colonize other planets or other star systems? Students are almost always interested in these questions, making it easy to motivate even those who study science only because it is necessary. These features account for the increasing amount of life in the universe courses offered at high school and college levels. A course on life in the universe can be a wonderful experience for instructors, in addition to being fascinating to students. The interdisciplinary nature of the subject means that regardless of your specific scientific background, you are sure to learn something new when you teach an astrobiology course, at any level. As courses in astrobiology began to appear, instructors faced an immediate challenge. The interdisciplinary nature of the subject made it difficult to decide where emphasis should be placed. Over time, however, a general consensus emerged, favoring a rough balance between the various disciplines that contribute to studying life in the universe. A universe of life? The night sky glitters with stars, each with a sun similar to ours. Many stars possess planets, a few of which could closely resemble the planets in our solar system. It may seem hard to imagine that Earth could be the only home for life among these countless worlds. However, although the chance of life beyond Earth may appear quite reasonable, we do not yet know if it exists. Learning whether the universe is full of life holds enormous significance for how we view ourselves and our planet. If life is rare or non-existent in other places, we will view our planet with added wonder. If life is common, we will know that Earth is not quite as special as it may seem. If civilizations are widespread, we must acknowledge our place among many intelligent species. The profound implications of finding, or not finding, extraterrestrial life make the question of life beyond Earth an exciting topic of study. The main aim of this book is to provide you with the background necessary to comprehend new and thrilling advancements in the human endeavor to discover life beyond Earth. To achieve this, we will concentrate on the scientific issues that underpin the search for life. First, however, let us start with a brief introduction to the subject, so you will understand why it has become such a hot topic of scientific research. The possibility of life beyond Earth. Aliens are everywhere if you follow the popular media, Figure 1.1. Television starships, such as the Enterprise or Voyager, continually search the galaxy for new life, hoping it speaks English or a language similar enough for the universal translator. In Star Wars, aliens from numerous planets gather at bars to share drinks and stories, and presumably to marvel at the fact that they have greater similarities in their level of technology than do various nations on Earth. Closer to home, movies like Independence Day, Men in Black, and War of the Worlds feature brave Earthlings battling evil aliens, or, as in the case of Avatar, brave aliens battling evil humans. While numerous websites carry headlines about the latest alien landings, even serious newspapers and magazines run occasional articles about unidentified flying object sightings, or about claims that the United States government is hiding frozen alien corpses at Area 51. And a recent election in Denver, Colorado, included a ballot initiative that would have created an Extraterrestrial Affairs Commission. Scientists are also interested in aliens, although most scientists remain deeply skeptical about reports of aliens on Earth. Scientists are therefore searching for life elsewhere, looking for evidence of life in other worlds in our solar system, trying to learn whether we should expect to find life on planets orbiting other stars, and searching for signals broadcast by other civilizations. Indeed, the study of life in the universe is one of the most rapidly growing fields of active scientific research, largely because of its clear significance. The discovery of life of any kind beyond Earth would forever change our perspective on how we fit into the universe as a whole, and it would undoubtedly teach us much more about life here on Earth as well. What are we searching for? When we say we are searching for life in the universe, what are we truly looking for? Is it the kind of intelligent life portrayed in science fiction television shows and films? Is it something more akin to the plants and animals we observe in parks and zoos? Is it tiny, bacteria-like microbes? Or could it be something else 100% entirely? The answer is all of the above. When we search for extraterrestrial life or life beyond Earth, we are looking for any sign of life, whether simple, complex, or intelligent. We do not care if it looks exactly like life we're familiar with on Earth, or is dramatically different. However, we cannot answer what we seek unless we know what life is. Unfortunately, defining life is a complex process, even on this planet where many examples exist. Ask yourself, what common attributes make us think that a bacterium, a beetle, a mushroom, a tumbleweed, a maple tree, and a human are all alive, while we do not think the same of a crystal, a cloud, an ocean, or a fire? If you spend a small amount of time thinking about this question, you will start to appreciate its difficulty. For example, Life can move, but the same is true of clouds and oceans. Life can grow, but so can crystals. Life can reproduce and spread, but so can fire. We will explore how scientists try to answer this question and come up with a general definition of life. For now, it should be clear that this is a complicated question that affects how we search for life in the universe. Because of this definitional difficulty, the scientific search for extraterrestrial life in the universe generally presumes a search for life that is at least somewhat Earth-like, and that we could therefore recognize based on what we know from studying life on Earth. While science fiction fans may argue that this search is too narrow, we must begin with what we know. Is it reasonable to imagine life beyond our planet? The scientific search for life in the universe is a relatively recent development in human history. But the idea of extraterrestrial life is not new. Numerous ancient cultures recounted tales of beings residing among the stars. And, as we will discuss, the ancient Greeks participated in serious philosophical debates regarding the possibility of life beyond Earth. Until recently, however, all these ideas remained purely speculative, because there was no way to study the question of extraterrestrial life scientifically. It was always possible to imagine extraterrestrial life, but there was no scientific reason to think it could exist. Indeed, scientists often misinterpreted the relatively small amounts of data that could have shed some light on life beyond Earth. Before the 20th century, for example, some scientists guessed that Venus might harbor a tropical paradise. A guess based on little more than the fact that Venus is covered by clouds and closer than Earth to the Sun. Mars was the subject of even more intense debate, largely because a small number of scientists thought they saw long, straight canals on the surface. People cited the non-existent canals as proof of a Martian civilization. Today, we have enough telescopic and spacecraft photos of the planets and large moons in our solar system to be quite confident that no civilization has ever existed on any of those. The prospect of large animals or large plants seems unlikely. Nevertheless, scientific interest in life beyond Earth has exploded in recent decades. Why? We will spend most of the book answering this question, but we can summarize the key points briefly. First, although large multicellular life in our solar system seems unlikely anywhere but on Earth, new planetary science and biology discoveries have given us some reason to think that simpler life, perhaps tiny microbes, might yet exist on other planets or moons that orbit our Sun. Secondly, while we have long known that the universe is full of stars, we have only recently gained concrete evidence that it is also full of planets, meaning there are many more places to search for life. Third, advances in scientific understanding and technology now make it possible to study the question of life in the universe through established scientific techniques, something that was not possible just a couple of decades ago. For example, we now understand enough about biology to explore the conditions that might make life possible in other worlds, and we know enough about planets to consider which ones might be capable of harboring existence. Indeed, while we have only a limited ability to search for life beyond Earth, we are rapidly developing the spacecraft technology needed to search for microbes in other worlds of our solar system, and the telescope technology needed to look for signs of life among the stars. Despite the possibility that life solely exists on Earth, there are now many scientific reasons to believe that it could be widespread, and that we could detect it if it is present. In the remainder of this chapter, we will briefly discuss the scientific context of the search and the locations where we might look for life, so you will understand what we cover in greater depth in the rest of the book. The scientific context of the search. Nearly every field of scientific research has at least a little connection to the quest for life in the universe. Even seemingly unrelated fields, such as mathematics and computer science, play important roles. For example, we use mathematics to do the many computations that help us understand all other areas of science, and we use computers to simulate everything from the formation of stars and planets to how the molecules of life interact with one another. However, three disciplines play an especially important role in framing the context of the scientific search for life: astronomy, planetary science, geology and atmospheric science, and biology. How does astronomy assist us in comprehending the possibilities for extraterrestrial life? For most of human history, our understanding of the universe varied from what it is now. Earth was widely assumed to be the center of the universe. Planets were lights in the sky named for ancient gods. No one thought they could be sites of life. Stars, unlike planets, were fixed in constellation patterns, and not many considered the possibility that our sun could be one of those. When the sun and planets were thought to orbit Earth, there was no reason to think stars could have planets, much less life-bearing ones. When you consider the dominance that this Earth-centered or geocentric view of the universe has held for many years, it becomes obvious that astronomy plays a key role in framing the context of the modern search for life. How and why did the human view of the cosmos change dramatically about 400 years ago? We will consider the modern astronomical context in some detail in Chapter 3. But the point should already be clear. We now know that Earth is one tiny world, orbiting one rather ordinary star in a vast cosmos, which opens up countless possibilities for life on other worlds. Astronomy provides context to the search for life in many other ways as well. But one more is important enough to mention right now. By studying distant objects, we have learned that the physical laws that operate in the rest of the universe are the same as those that operate right here on our planet. This tells us that if one thing happened here, the same could have happened somewhere else, at least in principle. We are not the center of the universe in location, and we have no reason to think we are central in any other way. How does planetary science assist us in comprehending the possibilities for extraterrestrial life? Planetary science is the term we use to study nearly all planet-related aspects. It includes the study of planets themselves, moons orbiting planets, how planets form, and other objects that may form in association with planets, such as asteroids and comets. Planetary science helps set the context for the search for life in the universe in several ways, but two are especially important. By learning how planets form, we initially comprehend how common we might anticipate them to be. In the middle of the last century, we had no reason to expect planets from numerous other stars. Several scientists thought this likely while others did not, and we lacked the data needed to distinguish between the two possibilities. However, during the second half of the 20th century, increasing comprehension of the processes by which our solar system formed, much of it grounded in evidence gathered through human visits to the moon and spacecraft visits to other planets, slowly made it appear more probable that other stars might likewise be born with planetary systems. Still, as recently as 1995, no one was sure whether planets existed around other stars. That was the year in which the first strong evidence was obtained for the existence of extrasolar planets, or planets orbiting stars other than our Sun. Since then, additional discoveries of extrasolar planets have poured in at an astonishing rate, so that the known extrasolar planets far outnumber the planets of our solar system. Based on the statistics of these discoveries, it now seems likely that many or most stars have planets, and it seems reasonable to imagine that life, and possibly even civilizations, could exist on at least some of these planets or their moons. The second way planetary science shapes the context for the search for life is by helping us understand how planets function. For example, by studying and comparing planets, we have learned why some planets are rocky, such as Earth, while others, such as Jupiter, contain vast amounts of hydrogen and helium gas. We have also learned why Venus is so hotter than Earth, even though, in the scheme of our solar system, it is just a little closer to the Sun. Similarly, we can now explain why the Moon is desolate and barren, even though it orbits the Sun at essentially the same distance as Earth. And we have a fairly good idea of why Mars is cold and dry today, when evidence shows that it was warmer and wetter in the distant past. This understanding of how planets work gives us deeper insight into the nature of planetary systems. More important to our purpose, it also helps us understand what to look for as we search for habitable worlds. Worlds that contain the necessities for life. Since there are more worlds in the universe than we can study in detail, constraining the search for promising ones can enhance our chances of discovering life. Be sure to note that when we ask whether a world is habitable, we inquire whether it offers environmental conditions under which life could arise or survive, not whether it actually harbors it. Also, remember that when we say a world is habitable, we do not necessarily mean that plants, animals, or people could survive in that environment. For much of Earth's history, almost all life was microscopic, and even today, the total mass of microbes on Earth is greater than that of all plants and animals combined. The search for habitable worlds is primarily a search for places where microbes of some kind might survive, though we might find larger organisms as well. Astronomy, planetary science, and other science disciplines play important roles in shaping the context of the search for life in the universe. But since we are searching for life, the context of biology is especially important. Just as you would not look for a house to buy without knowing about real estate, it would make no sense to search for life if we did not know how it functions. The key question about the biological context of the search revolves around whether we should expect biology to be rare or common in the universe. Wherever we look at the universe, we find clear evidence that the same laws of nature operate. We see galaxies spiral throughout space, and the same stellar processes in one location also occur in others. When we can observe orbital motions, they agree with what we expect from the law of gravity. These and other observations make us confident that the basic laws of physics we have discovered here on Earth also hold throughout the universe. We can be similarly confident that the laws of chemistry are universal. Observations of distant stars show that they are made of the same chemical elements that we find here in our solar system, and that interstellar gas clouds contain many of the same molecules we encounter on Earth. This provides conclusive evidence that atoms come in the same types and combine in the same ways throughout the universe. The universality of physics and chemistry makes us confident that we will find planets and other worlds, including many that are potentially habitable, throughout our Milky Way galaxy and the universe. Could biology also be universal? Could the biological processes we find on Earth be common throughout the universe? If affirmative, the quest for life beyond our planet should be thrilling and rewarding. If the answer is no, then life may be a rarity. We do not know whether biology is universal because we have not yet observed it anywhere beyond Earth. However, evidence from our planet gives us reason to think it may be. Experiments in the laboratory demonstrate that the chemicals present on Earth at the start would have easily combined to create complex organic, carbon-based molecules vital for life. Indeed, scientists have discovered organic molecules in meteorites, chunks of rock that fall to Earth from space, and through spectroscopy in clouds of gas between the stars. The fact that such molecules form even under the extreme conditions of space suggests that they form quite readily and may be common in numerous worlds. Of course, the mere presence of organic molecules does not necessarily mean that life will arise. But the history of life on Earth makes us think that the step from chemistry to biology is not especially difficult. As discussed in Chapter 6, geological evidence tells us that life on Earth arose quite early in Earth's history, at least on a geological timescale. This early origin of life on Earth suggests but certainly does not prove, that the same process might occur in other worlds. If the transition from chemistry to biology were exceedingly improbable, we might expect it would have required significantly more time. Thus, life's early origin, life Earth, makes it reasonable to think it would emerge just as swiftly on other worlds with similar conditions. The only remaining question is the prevalence of those right conditions, whether life can emerge under the appropriate conditions. Recent discoveries also give us reason to think that biology could be widespread. In particular, biologists have found that microscopic life can survive and prosper under a much wider range of conditions than was believed only a few decades ago. For example, we now know that life exists in boiling water near deep-sea volcanic vents, in the frigid conditions of Antarctica, and inside rocks buried 1 kilometer or more beneath the Earth's surface. It seems possible that some of these strange organisms could survive if we exported them from Earth to Mars or Europa. This suggests that the range of right conditions for life is quite broad. In this case, it might be possible to find life even on planets significantly different from Earth. In summary, we have no reason to think that life is rare, and there are several reasons to expect that it may be quite common. If life is life, studying it will provide us with new insights into life online, even if we do not find other intelligent civilizations. These enticing prospects have captured the interest of scientists from numerous disciplines around the globe, giving birth to a new science devoted to studying and searching for life in the universe. Studying life in the universe involves fundamental research in all the mentioned scientific areas. Indeed, as you will see throughout this book, the study of life in the universe goes far beyond simply searching for living organisms. Still, all of this study is driven by the possibility that life exists elsewhere. So before we dive into any details, it is worth a quick overview of the places and methods we use to search for life on Earth. Where should we search for life in the universe? The search for life in the universe occurs on several different levels. First and foremost, in many ways, it is a search for life here on this planet. As we discussed earlier, we are still learning about the various places and conditions under which life exists on Earth. And many scientists are busy searching for new species of life in the world. After all, the more we know about life, the better we can search for it elsewhere. Searching our solar system. Turning our attention to places besides Earth, our solar system is the first place to search for life in other worlds. Our solar system has many worlds, planets and dwarf planets, including Pluto and Eris, orbiting the Sun, moons orbiting planets, and countless smaller objects, such as asteroids and comets. The photos make clear how different Earth is from every other planet in our solar system. Our planet is the only one with oceans of liquid water on its surface, which provides an instant clue about why Earth is home to so many forms of life. Water is essential to all land-based life. Liquid water is always necessary for life, though a few other liquids might serve in place of water. The necessity for water or another liquid restricts our exploration as we pursue Earth-like life. Among the planets, Mars is the most promising candidate. As we will discuss in Chapter 8, strong evidence tells us that the now barren surface of Mars once had flowing water, making it seem reasonable to imagine life had arisen on Mars at that time. Mars still has significant amounts of water ice, so life exists today, perhaps hidden away in places where volcanic heat keeps underground water liquid. Life from the past or present is less likely to exist on other planets. Aside from the planets, a few large moons are the most promising abodes for life in the solar system. At least 6 moons are potential candidates for life. Life's best candidate is Jupiter's moon, Europa. Current evidence strongly suggests that Europa conceals a deep ocean of liquid water beneath its icy crust. Indeed, if we're interpreting the evidence correctly, The European Ocean may have significantly more water than all of Earth's oceans combined. We suspect life on land started in the deep oceans. Europa may have all the conditions for life and its ongoing survival. 2 additional moons of Jupiter, Ganymede and Callisto, also display some evidence of subsurface oceans. However, the evidence is weaker, and other considerations, primarily energy availability, give them poorer prospects for harboring life. The largest candidate for a life-bearing moon is Titan, which orbits Saturn, and is the only moon in the solar system with a substantial atmosphere. The Cassini spacecraft, which orbits Saturn, has revealed lakes of liquid methane on Titan's surface. Titans may also have liquid water deep underground, though any water on their surface must be frozen solid. Though lifeless, Titan has intriguing organic chemistry according to studies. The 5th and 6th moons for which we have found evidence of subsurface liquids, possibly liquid water, are Saturn's moon, Enceladus, and Neptune's moon, Triton. Searching among the stars. Regarding numbers, there are many more places to look for life on life nets and moons around other stars than in our solar system. However, the incredible distances to the stars make searches of these worlds much more difficult. All stars are so far away that we will need enormous leaps in technology to have any hope of sending spacecraft to study their planets up close. For example, with current spacecraft, the journey to even the nearest stars would take nearly 100,000 years. With visits out of reach, telescopic searches represent our only hope of finding life on life-solar worlds. Current telescope technology can detect extrasolar planets only under specific conditions. However, technology is advancing rapidly, and within a few decades we may have telescopes that can obtain crude pictures and spectra of planets and moons around other stars. As a result, one important area of research is trying to figure out the photographic or spectral signatures that would tell us we are looking at a world with life. Will alien life be searching for us? So far, we have talked about searching for a life that is not searching for us. That is, we could identify it only by seeing it with our spacecraft or telescopes. But if life is life on Earth, there could be other places like Earth, where life has resolved to become intelligent enough to be interested in searching for life in its home world. In that case, other civilizations might be broadcasting signals we could detect. The search for extraterrestrial intelligence, or SETI, which we will discuss in Chapter 12, focuses on searching for signals from alien civilizations. Although we do not know whether the search will meet with success, we can be sure that the unambiguous receipt of an alien message would be one of the most significant discoveries in human history. Not to mention the fact that it would also probably answer many of our other questions about life in the universe. We have seen that the study of life in the universe is a multidisciplinary field of scientific research involving scientists trained in many different specialties. Nevertheless, because it has become a prominent and important area of study, giving the science of life in the universe its name would be beneficial. Many different names are used, including exobiology and astronomy. But in this film, we follow the lead of NASA and call it astrobiology. This term combines astronomy, the study of the universe, with biology, which is the study of life. Astrobiology means the study of life in the universe. How do we study the possibility of life existing on Earth? Because astrobiology is a young science, scientists are still deciding where to focus their research efforts. One major player in this effort is the NASA Astrobiology Institute, a collaboration involving scientists from NASA and more than 12 other research institutions across the United States. Similar efforts are underway in other countries, including the United Kingdom, Sweden, France, Spain, Russia, and Australia. These collaborations are among the most interdisciplinary in any area of science, bringing together astronomers, biologists, geologists, chemists, and many others seeking to understand the prospects of finding life on Earth. Although various groups concentrate on various issues, The following three areas represent the majority of astrobiology research. 1. Studying the conditions conducive to life's lives and ongoing existence. 2. We are looking for such conditions on other planets in our solar system and around other stars. 3. Looking for the actual occurrence of life elsewhere. Therefore, astrobiology includes more than simply searching for extraterrestrial life or civilizations. At a fundamental level, astrobiology research seeks to reveal the connections between living organisms and the places where they reside. In this sense, finding no life, on Mars, for example, is just as significant a result as finding life. Either way, we learn about the conditions that can lead to the presence of life, how life lives in conjunction with planets, and about whether existence is likely to be rare or common throughout the universe. Along the way, we will learn what science can say about the future of life on Earth, consider possible futures for our species, and discuss the philosophical implications of the search for, and potential discovery of, life on Earth. Despite abundant aliens in popular media, we have no convincing evidence for life on Earth. However, what we know now about astronomy, planetary science, and biology makes it seem reasonable to think that life is common. Finding this life on other planets would significantly impact our understanding of a universe full of living things. Life is conceivable on several worlds in our solar system, but it is unlikely that any of this life is intelligent. However, we find many more possibilities when considering life on planets or planets around other stars. Through the search for extraterrestrial intelligence, SETI, we could receive a signal from an advanced civilization. The prospect that life is common in the universe has given rise to the new science of astrobiology, an exciting and interdisciplinary field of research that focuses on understanding the possibility of finding existence elsewhere and on the actual search for life on Earth. Extraterrestrial life is akin to a contemporary concept, yet tales of life on Earth extend far back into ancient eras. Numerous stories revolved around mythical or supernatural entities residing among the constellations, but some were not so dissimilar from our current notions. Nonetheless, the current quest for life in the living universe diverges from ancient conjectures significantly. While ancient individuals could do little more than speculate about the likelihood of discovering life elsewhere, we can now examine this possibility with the robust techniques of modern science. How can we study life in the universe without knowing anything about life beyond Earth? The answer is that we use science to help us understand the conditions under which we expect to find life, the characteristics of life here, and the methods we can use to search for it. Because the methods of science are so integral to the search for life on Earth, we devote the ancient debate about life beyond Earth. Ancient Greek scholars engaged in a lively debate about the possibility of life beyond Earth more than 2,300 years ago. Several scholars argued that there must be life elsewhere, while others, particularly Aristotle, contended the opposite. This impassioned debate may seem like a historical curiosity in some ways, but the fact that it occurred tells us that a significant change in human thinking was already underway. Deeper in the past, our ancestors looked at the sky and attributed what they saw to the arbitrary actions of mythological beings, an idea still reflected in the fact that the planets carry the names of mythological gods. In contrast, the Greek scholars sought rational explanations for what they could observe in the universe surrounding them. As far as we know, these Greek efforts marked the first attempts to understand the universe through methods closely resembling the ones we use in science today. Thus, if we want to understand how modern science works and how we can use it to study the possibility of life beyond Earth, we must begin by peering more than 2,000 years into the past, to see how observations of the sky started humanity on the road to modern science and kindled interest in the question of whether the universe is ours alone. How did attempts to understand the sky begin our journey towards science? Imagine living in ancient times, looking up at the sky without the benefit of our modern knowledge. What would you witness? The sun rises in the east and sets in the west each day, its precise path varying with the seasons. At night, the stars circle the sky, with various constellations prominent at various times of the year. The moon goes through monthly phases from new to full and back again, while the planets gradually meander among the stars in seemingly mysterious ways. All the while, the ground beneath you feels steady and solid. It would be natural to assume, as did people of many early cultures, that Earth is a flat, motionless disk surmounted by a dome-like sky across which the heavenly bodies move. The tale of how we advanced from this simple, intuitive perspective of Earth and the heavens to our contemporary comprehension of Earth as a tiny planet in a vast cosmos is, in numerous ways, the narrative of the evolution of science itself. Our ancestors were curious about numerous aspects of the world, but astronomy held a special interest. The sun plays a central role in our lives, governing daylight and darkness and the progression of the seasons. The connection of the moon to the tides would have been obvious to individuals living near the sea. The evident power of these celestial bodies probably explains why they played prominent roles in many early religions, and may be one reason why it seemed so important to know the sky. Careful observations of the sky also served practical needs by enabling ancient peoples to keep track of the time and the seasons, crucial requirements for agricultural societies. As civilizations rose, astronomical observations became more careful and elaborate. In some cases, the results were recorded in writing. The ancient Chinese kept detailed records of astronomical observations beginning some 5,000 years ago. By about 2,500 years ago, written records allowed the Babylonians, in the region of modern-day Iraq, to predict eclipses with enormous success. Halfway around the world, and a few centuries later, the Mayans of Central America independently developed the same ability. These ancient recorded astronomy observations represent databases of facts, the raw material of science. However, in the majority of instances for which we possess historical records, it seems that these facts were never utilized for much beyond fulfilling immediate religious and practical needs. The clear exception was ancient Greece, where scholars attempted to use these facts to understand the architecture of the universe. Greece gradually rose as a power in the Middle East, beginning around 800 BC, and was well established by around 500 BC. Greece's strategic location served as a crossroads for travelers, merchants and armies from northern Africa, Asia and Europe building. On the diverse ideas brought forth by the meeting of these many cultures, ancient Greek philosophers began to move the human understanding of nature from the mythological to the rational. We generally trace the origin of Greek science to the philosopher Thales, who lived around 624 to 546 BC, pronounced Thales. Among his many accomplishments, Thales was the first person known to have addressed the question, "What is the universe made of?" without resorting to supernatural explanations. His own guess, that the universe fundamentally consisted of water, and that Earth was a flat disk on an infinite ocean, was not widely accepted even in his own time. But his mere asking of the question helped set the stage for all later science. For the first time, someone had suggested that the world was inherently understandable and not just the result of arbitrary or incomprehensible events. Others, perhaps most famously Plato, who lived from 428 to 348 BC, and his student Aristotle, who lived from 384 to 322 BC, continued the scholarly tradition Thales started. Each Greek philosopher introduced new ideas, at times in contradiction to the ideas of others. None of these ideas rose quite to the level of modern science, primarily because the Greeks tended to rely more on pure thought and intuition than on observations or experimental tests. Nevertheless, with hindsight, we can see at least three major innovations in Greek thought that helped pave the way for modern science. Initially, the Greek philosophers established a tradition of seeking to comprehend nature without turning to supernatural explanations. For example, although earlier Greeks might have accepted that the sun moves across the sky because it is pulled by the god Apollo in his chariot, an idea whose roots were already lost in antiquity, the philosophers sought a natural explanation that caused them to speculate anew about the construction of the heavens. They were free to think creatively because they were not simply trying to prove preconceived ideas, and recognized that new ideas should be open to challenge. As a result, they often worked together, debating and testing one another's proposals. This tradition of challenging almost every new idea remains one of the distinguishing features of scientific work today. Secondly, the Greeks developed mathematics in the form of geometry. They appreciated this discipline for its intrinsic value and recognized its potential, employing geometry to address both engineering and scientific challenges. Without their mathematical sophistication, they would not have gone far in their attempts to understand the cosmos. Like the Greek tradition of challenging ideas, the use of mathematics to help explore the implications of new ideas remains an important part of modern science. Third, while much of their philosophical activity consisted of subtle debates with little connection to observations or experiments, the Greeks also understood that an explanation about the world could not be correct if it disagreed with observed facts. This willingness to discard explanations that do not work is also a crucial part of modern science. The geocentric model, perhaps the greatest Greek contribution to science, came from the way they synthesized all three innovations into creating models of nature, which is still central to modern science. Scientific models differ somewhat from those you might be accustomed to on a daily basis. Each day, we consider models as small physical representations, like model cars or airplanes. In contrast, a scientific model is a conceptual representation that aims to explain and predict observed phenomena. For example, a model of Earth's climate uses logic, mathematics, and known physical laws to represent how the climate functions. Its purpose is to explain and predict climate changes, such as the ones that may occur with global warming. Just as a model airplane does not faithfully represent every aspect of a real airplane, a scientific model may not fully explain all our observations of nature. Nevertheless, even the failings of a scientific model can be useful because they often point the way toward building a superior model. In astronomy, the Greeks constructed conceptual models of the universe to explain what they observed in the sky, an effort that quickly led them past simplistic ideas of a flat Earth under a dome-shaped sky to a far more sophisticated view of the cosmos. Anaximander, around 600 to 547 BC, a student of Thales, took one of the first crucial steps. In an attempt to explain how the sky appears to turn around the pole star, each day, Anaximander suggested that the heavens must form a complete celestial sphere around Earth. Moreover, based on how the sky varies with latitude, he realized that Earth's surface must be curved, though he correctly guessed Earth to be a cylinder rather than a sphere. The idea of a round Earth probably followed soon, and by around 500 BC, it was part of the teachings of Pythagoras, circa 560 to 480 BC. He and his followers most likely adopted a spherical Earth for philosophical reasons. The Pythagoreans had a mystical interest in mathematical perfection and considered a sphere geometrically perfect. More than 100 years later, Aristotle cited observations of Earth's curved shadow on the moon during lunar eclipses as evidence for a spherical Earth. Greek philosophers adopted a geocentric universe model. Recall that geocentric means Earth-centered, with a spherical Earth at the center of a massive celestial sphere. Incidentally, this shows the error of the widespread myth that Columbus proved Earth to be round when he sailed to America in 1492. Not only were scholars of the time well aware of Earth's round shape, But they even knew Earth's approximate size. Earth's circumference was first measured fairly accurately in about 240 BC by the Greek scientist Eratosthenes. In fact, Columbus likely faced significant difficulties in finding a sponsor for his voyages, due to his erroneous claim that the distance by sea from Western Europe to Eastern Asia was much shorter than what the scholars knew. His erroneous belief would nearly certainly have led his voyage to disaster if the Americas had not stood in his way. If you closely observe the sky, you will notice that the Sun, the Moon, and the 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, gradually move among the constellations from day to day, even though the patterns of the constellations appear to remain constant. Indeed, the word planet comes from the Greek for wanderer. It originally referred to the Sun and Moon, and the 5 visible planets. Our week of 7 days is directly traceable to the fact that 7 planets are visible in the heavens. The wanderings of these objects convinced the Greek philosophers that there had to be more to the heavens than just one single sphere surrounding Earth. The Sun and Moon each move steadily through the constellations, with the Sun completing a circuit around the celestial sphere each year, and the Moon completing each circuit in about a month, which can be thought of as a moonth. The Greeks could account for this motion by adding spheres for the Sun and Moon, each nested within the sphere of the stars, and allowing these spheres to turn at different rates from the sphere of the stars. But the 5 visible planets posed a much greater mystery. If you observe the position of a planet such as Mars or Jupiter relative to the stars over several months, you will find not only that its speed and brightness vary considerably, but that its direction of motion sometimes also changes. While the planets usually move eastward relative to the constellations, sometimes they reverse course and go backward. These periods of apparent retrograde motion, retrograde means backward, last from several weeks to several months, depending on the planet. This seemingly erratic planetary motion was not so easy to explain with rotating spheres, especially because the Greeks generally accepted a notion of heavenly perfection, enunciated most clearly by Plato, which demanded that all heavenly objects move in perfect circles. How could a planet sometimes move backward when traveling in a perfect circle? The Greeks came up with several clever ideas that kept Earth in the center of the universe. The astronomer Ptolemy, who lived around 100 to 170 years ago and is pronounced Ptolemy, developed the most complicated model of how planets move around the Sun. We call this model the Ptolemaic model, to differentiate it from earlier geocentric models. This model reproduced retrograde motion by having planets move around Earth in small circles that turned around larger circles. A planet following this circle-on-circle motion traces a loop as seen from Earth, with the backward portion of the loop mimicking apparent retrograde motion. The circle-on-circle motion may seem somewhat complex, but Ptolemy also had to use numerous other mathematical tricks, including placing some of the circles off-center to get his model to agree with observations. Despite all this complexity, he achieved remarkable success. His model could correctly forecast future planetary positions within a couple of degrees of arc, roughly equivalent to holding your hand at arm's length against the sky. Indeed, the Ptolemaic model generally worked so well that it remained in use for the next 1,500 years. When Arabic scholars translated Ptolemy's book describing the model around the year 1023, 800, they gave it the title Almagest, derived from words meaning the greatest compilation. In about 260 BC, the Greek scientist Aristarchus, circa 310 to 230 BC, offered a radical departure from the conventional wisdom. He suggested that Earth goes around the Sun, rather than vice versa. Little of Aristarchus's work survives to the present day, so we do not know exactly how he came up with his sun-centered idea. We do know that he made measurements that convinced him that the Sun is much larger than Earth, So perhaps he concluded that it was more natural for the smaller Earth to orbit the larger Sun. In addition, he almost certainly recognized that a sun-centered system offers a far more natural explanation for apparent retrograde motion. You can see how the sun-centered system explains retrograde motion with a simple demonstration. Find an empty area, such as a sports field or a big lawn, and mark a spot in the middle to represent the Sun. You can represent Earth by walking counterclockwise around the Sun, while a friend represents a more distant planet, such as Mars, Jupiter, or Saturn, by walking counterclockwise around the Sun at a greater distance. Your friend should walk more slowly than you, because more distant planets orbit the Sun with greater care. As you walk, observe how your friend seems to move in relation to the buildings or trees that are far away. Although you always walk in the same direction around the Sun, your friend will appear to move backward against the background during the part of your orbit where you catch up to and pass them. To understand the apparent retrograde motions of Mercury and Venus, which are closer to the Sun than Earth, switch places with your friend and repeat the demonstration. The demonstration applies to all the planets. For example, because Mars takes about 2 years to orbit the Sun, actually 1.88 years, it covers about half its orbit during the 1 year Earth makes a complete orbit. If you trace lines of sight from Earth to Mars from different points in their orbits, you will see that the line of sight usually moves eastward relative to the stars, but moves westward when Earth is passing Mars in its orbit, figure 2.5b. Like your friend in the demonstration, Mars never actually changes its direction. It only seems to change direction from our viewpoint on Earth. Despite the elegance of this sun-centered model for the universe, Aristarchus had little success convincing his contemporaries to accept it. Several reasons for this rejection were purely philosophical and not based on solid evidence. However, at least one major objection was firmly rooted in observations. Aristarchus's idea seemed inconsistent with observations of stellar positions in the sky. To understand the inconsistency, imagine what would happen if you placed the Sun rather than Earth at the center of the celestial sphere, with Earth orbiting the Sun a certain distance away. In that case, Earth would be closer to various portions of the celestial sphere at different times of the year. The stars on a part of the sphere appeared more widely separated when we were closer to it, just like the spacing between a car's headlights when you're closer. This would create yearly shifts in the separations of stars. But the Greeks observed no such shifts. They only had 2 explanations for the lack of a shift. Earth was at the center of the universe, or the stars were too far away to see. To most Greeks, it seemed unreasonable to imagine that the stars could be so far away, which inevitably led them to conclude that Earth must hold a central place. This argument about stellar shifts still holds when we allow for the reality that stars lie at different distances, rather than all on the same sphere. As Earth orbits the Sun, we look at particular stars from slightly different positions at different times of year, causing the positions of nearby stars to shift slightly relative to more distant stars. Although such shifts are much too small to measure with the naked eye, because stars are very far away, they are easily detectable with modern telescopes. These annual shifts in stellar position, referred to as stellar parallax, now demonstrate that Earth orbits the Sun. The roots of modern science. Although the Greeks ultimately rejected the correct idea that Earth orbits the Sun, we see that they did so for reasons that made good sense at the time. Not all of their reasons would pass the test of modern science. For example, their preference for motion in perfect circles came only from their cultural ideas of aesthetics, and not from any actual data. But they also went to numerous forts to ensure that their models were consistent with observations, and in that way, they laid the foundation of modern science. Even though Aristarchus did not achieve success during his own time, his idea continues to live on in literary works. Some 1,800 years after he first proposed it, Aristarchus's sun-centered model apparently came to the attention of a Polish astronomer named Nicholas Copernicus, who took the idea and ran with it in a way that led directly to the development of modern science. We will return to this story shortly. Why did the Greeks argue about the possibility of life beyond Earth? Thales' question about the composition of the universe arose almost from the Earth, and the Greeks understood that the answer would influence life in other places. This may seem surprising considering their geocentric beliefs, because they did not perceive the planets or stars as worlds in the manner we understand them today. Instead, the Greeks generally considered the world to include both Earth and the heavenly spheres that they imagined to surround it, and they were at least open to the possibility that other such worlds might exist. As we noted earlier, Thales guessed that the world consisted fundamentally of water, with Earth floating on an infinite ocean. But his student Anaximander imagined a more mystical element that he called apeiron, meaning infinite. Anaximander suggested that all material things arose from and returned to the apeiron, which allowed him to imagine that worlds might be born and repeatedly die through eternal time. So even though he made no known claim of life existing elsewhere in the present, Anaximander essentially suggested that other Earths and other beings might exist at other times. Other Greeks took the debate in a slightly different direction, and eventually a consensus emerged in favor of the world being built from 4 elements: fire, water, earth, and air. However, different schools of thought emerged regarding the nature and extent of these elements. The atomists held that Earth and the heavens were made from an infinite number of indivisible atoms of each of the 4 elements. The Aristotelians, following Aristotle, believed that the 4 elements, not necessarily composed of atoms, were limited to the domain of Earth, while the heavens were made of a separate 5th element, often referred to as the ether, or the quintessence, literally the 5th essence. The differences in the 2 schools of thought led to 2 fundamentally different conclusions about the possibility of extraterrestrial life. The atomist doctrine was developed largely by Democritus, who lived around 470 to 380 BC, and his views show how the idea led almost inevitably to belief in extraterrestrial life. Democritus argued that the world, Earth and the heavens, is created by the random motions of finite atoms. Because this idea held that the total of atoms was infinite, it was natural to assume that the same processes that created our world could also have created others. A later atomist, Epicurus, who lived from 341 to 270 BC, clearly described this philosophy on life beyond Earth in the following quotation: "There are infinite worlds, both like and unlike this one. We must believe that in all worlds there are living creatures, plants, and other things we see in this one." Aristotle held a different perspective. He believed that each of the 4 elements had its own natural motion and place. For example, he believed that the element Earth moved naturally toward the center of the universe, an idea that explained the Greek assumption that Earth resided in a central place. He claimed that the element of fire naturally rose away from the center, explaining why flames jut upward into the sky. These incorrect ideas about physics, which were not disproved until the time of Galileo and Newton almost 2,000 years later, caused Aristotle to reject the atomist idea of many worlds. More than a single world would mean more than one natural place for the elements, which is illogical. Aristotle concluded, "The world must be one of a kind. There cannot be multiple worlds." Interestingly, Aristotle's philosophies were not particularly influential until several centuries after his death. His books were preserved and valued, in particular by Islamic scholars of the late first millennium. But they were unknown in Europe until they were translated into Latin in the 12th and 13th centuries. St. Thomas Aquinas, born in the year 1225 and passing in the year 1274, integrated Aristotle's philosophy into Christian theology. At this point, the contradiction between the Aristotelian notion of one world and the atomist notion of many worlds became a major concern to Christian theologians. Moreover, atomism became associated with atheism, because the atomist view held that our world came into existence through random motions of atoms, without the need for any intelligent creator. The debate about extraterrestrial life thus became intertwined with debates about religion. Even today, the theological issues are not fully settled, and echoes of the ancient Greek debate between the atomists and the Aristotelians still reverberate in our time. The Copernican Revolution. Greek ideas gained enormous influence in the ancient world, in large part because the Greeks proved to be as adept at politics and war as they were at philosophy. In about 330 BC, Alexander the Great began a series of conquests that expanded the Greek Empire throughout the Middle East. Alexander was interested in science and education, perhaps because he grew up with Aristotle as his tutor. Alexander established the city of Alexandria in Egypt, which soon became home to the greatest library the world had ever seen. The Library of Alexandria remained the world's preeminent research center for 700 years. At its peak, the library may have held more than 500,000 books, all handwritten on papyrus scrolls. A time of anti-intellectual fervor in the 5th century AD finally destroyed the library, erasing most ancient Greek writings for eternity. The rise of a new center of intellectual achievement in Baghdad, located in present-day Iraq, would have prevented the loss of many more. While European civilization fell into the Dark Ages, scholars of the new religion of Islam sought knowledge of mathematics and astronomy in hopes of better understanding the wisdom of Allah. The Islamic scholars translated and preserved numerous ancient Greek works that remained. Building on what they learned from the Greek manuscripts, they went on to develop the mathematics of algebra and numerous new instruments and techniques for astronomical observation. The Islamic world of the Middle Ages was in frequent contact with Hindu scholars from India, who in turn brought ideas and discoveries from China. Hence, the intellectual center in Baghdad achieved a synthesis of the surviving work of the ancient Greeks, the Indians, the Chinese, and the contributions of its own scholars. This accumulated knowledge spread throughout the Byzantine Empire, which was the eastern part of the former Roman Empire. When the Byzantine capital of Constantinople, which is modern-day Istanbul, fell in 1453, many Eastern scholars headed west to Europe, carrying with them the knowledge that helped ignite the European Renaissance. The stage was set for dramatically rethinking humanity and our position in the universe. How did the Copernican revolution advance the progress of science? In 1543, Nicholas Copernicus published De Revolutionibus Orbium Coelestium, concerning the revolutions of the heavenly spheres, launching what we now call the Copernican revolution. In his book, Copernicus revived Aristarchus's radical suggestion of a sun-centered solar system and described the idea with enough mathematical detail to make it a valid competitor to the Earth-centered Ptolemaic model. Over the next 150 years, philosophers and scientists, often one and the same, debated and tested the Copernican idea. Numerous ideas that now form the foundation of modern science first arose as this debate played out. Indeed, the Copernican revolution had such a profound impact on philosophy that we cannot understand modern science without first understanding the key features of this revolution. By the time of Copernicus's birth in 1473, tables of planetary motion based on the Ptolemaic model had become noticeably inaccurate. However, a small number of people were willing to undertake the difficult calculations required to revise the tables. Indeed, the best tables available were already 200 years old, having been compiled under the guidance of the Spanish monarch Alfonso X, who lived from 1221 to 1284. Commenting on the tedious nature of the work involved, the monarch is said to have complained, "If I had been present at the creation, I would have recommended a simpler design for the universe." Copernicus began studying astronomy in his late teens. He soon became aware of the inaccuracies of the Ptolemaic predictions and began a quest for a better way to predict planetary positions. He adopted Aristarchus's sun-centered idea, likely due to its straightforward explanation of the planet's apparent retrograde motion. As he worked out the mathematical details of his model, Copernicus discovered simple geometric relationships that allowed him to calculate each planet's orbital period around the Sun and its relative distance from the Sun in terms of Earth-Sun distance. The success of his model in providing a geometric layout for the solar system further convinced him that the Sun-centered idea must be correct. Despite his own confidence in the model, Copernicus hesitated to publish his work, fearing that the idea of a moving Earth would be considered absurd. However, he discussed his system with other scholars, including high-ranking officials of the Church, who urged him to publish a book. Copernicus saw the first printed copy of his book on the day he died, May 24th, 1543. The book's publication widely disseminated the sun-centered idea, attracting many scholars due to its aesthetic advantages. Nevertheless, the Copernican model gained relatively few converts over the next 50 years. And for a good reason. It didn't work all that well. The primary problem was that while Copernicus had been willing to overturn Earth's central place in the universe, he had held fast to the ancient belief that heavenly motion must occur in perfect circles. This incorrect assumption forced him to add numerous complexities to his system, including circles on circles, much like those used by Ptolemy, to get it to make any reasonable predictions. In the end, his complete model was no more accurate and no less complex than the Ptolemaic model, and few people were willing to throw out thousands of years of tradition for a new model that worked just as poorly as the old one. Part of the difficulty faced by astronomers who sought to improve either the Ptolemaic or the Copernican model was a lack of quality data. The telescope had not yet been invented, and existing naked-eye observations were not particularly accurate. In the late 16th century, Danish nobleman Tycho Brahe, who lived from 1546 to 1601, usually known simply as Tycho, set about correcting this problem. Tycho was an eccentric genius who, at the age of 20, had lost part of his nose in a sword fight with another student over who was the better mathematician. Taking advantage of his royal connections, he built large, naked-eye observatories that worked much like giant protractors. And over 3 decades, he used them to measure planetary positions to within 1 minute of arc, 1 degree, which is less than the thickness of a fingernail held at arm's length. Tycho never fully satisfactorily explained his observations, though he made a valiant attempt. But he found someone else who did. In 1600, he hired a young German astronomer, Johannes Kepler, 1571 to 1630. Kepler and Tycho had a strained relationship, but in 1601, as he lay on his deathbed, Tycho begged Kepler to find a system that would make sense of his observations, so that it may not appear, "I have lived in vain." Kepler was deeply religious, and believed that understanding the geometry of the heavens would bring him closer to God. Like Copernicus, he believed that planetary orbits should be perfect circles, so he worked diligently to match circular motions to Tycho's data. After years of effort, he found a set of circular orbits that matched most of Tycho's observations well. Even in the worst cases for Mars, Kepler's predicted positions differed from Tycho's observations by only about 8 arc minutes. Kepler surely attempted to ignore these discrepancies and attribute them to Tycho's errors. After all, 8 arc minutes is barely 1/4 the angular diameter of the full moon. But Kepler trusted Tycho's careful work. The small discrepancies finally led Kepler to abandon the idea of circular orbits and to find the correct solution to the ancient riddle of planetary motion. About this event, Kepler wrote, "If I had believed we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy." Kepler's decision to trust the data over his preconceived beliefs marked an important transition point in the history of science. Once he abandoned perfect circles, he was free to try other ideas. and he soon hit on the correct one. Planetary orbits take the shapes of the special types of ovals known as ellipses. He then applied his mathematical knowledge to establish his new model of planetary motion, articulating its key features using what we now refer to as Kepler's laws of planetary motion. Kepler's first law. The orbit of each planet about the Sun is an ellipse with the Sun at one focus. This law tells us that a planet's distance from the Sun varies during its orbit. It is closest at the point called perihelion, from the Greek, for near the Sun, and farthest at the point called aphelion, from the Greek, for away from the Sun. The average of a planet's perihelion and aphelion distances is the length of its semi-major axis. We will refer to the Kepler's second law states that, as a planet moves around its orbit, it sweeps out equal areas at equal times. This means the planet moves farther near the perihelion than near the aphelion, which means it moves faster closer to the Sun and slower farther away. Kepler's third law states that more distant planets orbit the Sun at slower average speeds, following the precise mathematical relationship. P2 equals A3, where P is the planet's orbital period in years, and AN is its average distance, semi-major axis, from the Sun in astronomical units. One astronomical unit is defined as Earth's average distance from the Sun, or about 149.6 million kilometers. Kepler published his first two laws in 1609 and his third in 1619. Together, they created a model that could predict planetary positions more accurately than Ptolemy's Earth-centered model. Indeed, Kepler's model has performed so well that we now view it as an abstract concept and a tool that reveals a profound underlying truth about planetary positions. The success of Kepler's laws in matching Tycho's data provided strong evidence in favor of Copernicus's placement of the Sun, rather than Earth, at the center of the solar system. Nevertheless, numerous scientists still voiced reasonable opinions on the Copernican view. There were three basic objections to the 2,000-year-old beliefs of Aristotle. First, Earth could not be moving because if it were, objects such as birds, falling stones, and clouds would be left behind as Earth moved along its path. Second, the idea contradicted the view that the heavens, the realm of the Sun, Moon, planets, and stars, must be perfect and unchanging. Third, no one had detected that this should occur if Earth orbits the Sun. Galileo Galilei, born in 1564 and passing in 1642, is nearly always known by only his first name and answered all three objections. Galileo dispelled the initial objection through experiments that overturned the Aristotelian perspective on physics. In particular, he used experiments with rolling balls to demonstrate that a moving object remains in motion unless a force is applied, an idea now codified in Newton's first law of motion. This insight explains why objects that share Earth's motion through space, such as birds, falling stones, and clouds, should stay with Earth rather than fall behind, as Aristotle had argued. This idea explains why passengers remain with a moving airplane even when they leave their seats. Tycho's observations of a supernova and the proof that comets lie beyond the Moon in Galileo's time already challenged the notion of heavenly permanence, demonstrating that the heavens occasionally undergo upheaval. Galileo drove the new idea home after he built a telescope in the late 60s. Through his telescope, Galileo saw sunspots on the Sun. Sunspots were regarded as imperfections during that period. He also used his telescope to prove that the Moon has mountains and valleys like the imperfect Earth, by noticing the shadows cast near the dividing line between the light and dark portions of the lunar face. If the heavens were not perfect, elliptical orbits instead of circles would be easier to accept. The third objection, the absence of observable stellar parallax, had been a particular concern of Tycho's. Tycho's estimates of the distances. Tycho believed that his naked eye observations were sufficient to detect stellar parallax if Earth did, in fact, orbit the Sun. To refute Tycho's estimates, it was necessary to demonstrate that the stars were more distant than Tycho had initially believed, making it impossible for him to have observed stellar parallax. Although Galileo didn't prove this fact, he provided strong evidence in its favor. For example, he saw that the Milky Way resolved into countless individual stars with his telescope. This discovery helped him argue that the stars were far more numerous and distant than Tycho believed. In hindsight, the final nails in the coffin of the Earth-centered universe were two of Galileo's discoveries through the telescope. Galileo clearly observed 4 moons orbiting Jupiter, not Earth. Soon thereafter, he observed that Venus goes through phases in a way that proved that it must orbit the Sun and not Earth. Together, these observations prove that Earth is not the center of everything. While we now acknowledge Galileo's contributions, the story was more intricate during his era, when Catholic Church doctrine maintained that Earth was the center of the universe. A church inquisition in Rome brought Galileo before them on June 22, 1633, ordering him to retract his claim that Earth orbits the Sun. Nearly 70 years old and fearing for his life, Galileo complied. His life was spared. However, legend has it that as he rose from his knees, he whispered, "Eppur si muove, muove," Italian for "and yet it moves." Given the likely consequences if church officials had heard him say this, most historians doubt the legend. The church did not formally vindicate Galileo until 1992, but had long given up the argument. Today, Catholic scientists are at the forefront of much astronomical research, and official church teachings are compatible not only with the status of Earth's path, but also with the theories of the Big Bang and the subsequent evolution of the cosmos and of life. Ars model worked well, and Galileo successfully diffused the remaining objections. By approximately the 1630s, scientists were nearly unanimous in accepting the validity of Kepler's planetary motion. However, no one knew why the planets should move in elliptical orbits with different speeds. The question became a topic of lively debate, and several scientists even guessed the correct answer. But they could not prove it, largely because the understanding of physics and mathematics did not exist. This understanding finally came through the remarkable work of Sir Isaac Newton, 1642 to 1727, who invented the mathematics of calculus and used it to explain and discover many fundamental principles of physics. In 1687, Newton published a famous book, Principia, short for Philosophiae Naturalis, Principia Mathematica, Mathematical Principles of Philosophy. In it, he laid out precise mathematical descriptions of how motion generally works, ideas that we now describe as Newton's motion. Newton continued in Principia to describe the universal law of gravitation and used mathematics to prove Kepler's natural consequences of the laws of motion and gravity. While these observations proved that Earth is not the center of everything, they did not by themselves prove that Earth orbits the Sun. Direct proof of that fact did not come until later, with measurements of stellar parallax and of an effect known as the aberration of starlight, that also occurs only because of Earth's moon. Nevertheless, the existence of Jupiter's moons showed that moons can orbit a moving planet like Jupiter, which overcame some critics' criticism that the moon could not stay with a moving Earth. The proof that Venus orbits the Sun validates Kepler's sun-centered planetary motion. In essence, Newton created a new model for the universe's inner workings, in which motion is governed by clear laws and the force of gravity. The model explained much about everyday motion and planet movements, and the geocentric idea was no longer credible. More than 150 years passed between Copernicus's De Revolutionibus in 1543 and Newton's Principia in 1687. Such a short time in the scope of human history that we call it a revolution. A quick look back shows that the revolution not only caused a radical change in human perspective on our place in the universe, shifting Earth from a central role to being just one of many worlds, but also altered our ideas about how knowledge should be acquired. For example, while previous generations tolerated inaccuracies in the predictions of the Ptolemaic model, Copernicus and his followers felt compelled to find models of nature that could reproduce what they observed. The eventual success of Kepler's work led to a new emphasis on understanding why nature works as it does. Past generations had relied solely on their cultural senses of aesthetics, in guessing that the world was built with perfect circles, spheres, and indivisible atoms, and they seemed content to accept these guesses even without any evidence of their reality. By Newton's time, this was no longer good enough. Instead, one had to present hard evidence, backed by rigorous mathematics, to convince colleagues that one had hit something that brought us closer to understanding the nature of the universe. How did the Copernican revolution change the ancient debate on extraterrestrial life? The Copernican revolution did not deal directly with the question of life in the universe, but it affected how people thought about the issue. You can see why by thinking back to the ancient Greek debate. While the atomists believed there were many worlds, Aristotle believed this world must be unique, and in the center of everything because his physics convinced him that all the Earth in the universe would have fallen to the center. The Copernican revolution therefore proved that Aristotle was wrong. Earth is not the center of the universe after all. Of course, the fact that Aristotle was wrong did not mean that the atomists had been right. But many of the Copernican-era scientists assumed they had been. Galileo suggested that lunar features he saw through his telescope might be land and water, like that on Earth. Kepler concurred and proposed that the moon possessed an atmosphere and was home to sentient entities. Kepler even wrote a science fiction story, Somnium, the Dream, in which he imagined a trip to the Titans. Giordano Bruno was so convinced of the existence of extraterrestrial life that he battled authorities. They finally had him burned at the stake. Subsequently, scientists advanced the atomist belief even further. William Herschel, born in 1738 and passing in 1822, was renowned for his co-discovery of Uranus alongside his sister Caroline. He believed that all planets supported life. In the late 19th century, when Percival Lowell, born in 1855 and passing in 1916, believed he saw canals on Mars, it is quite likely that he was still influenced by the philosophical ruminations of people who had lived more than 2,000 years earlier. If this debate about extraterrestrial life shows anything, it is probably possible to argue almost endlessly, as long as there are no actual facts to get in the way. With hindsight, it is easy to see that everything from the musings of the ancient Greeks to Lowell's canals was based more on hopes and beliefs than on any real evidence. Nevertheless, the Copernican revolution marked a significant shift in the debate regarding extraterrestrial life. For the first time, we tested one of the ancient ideas, Aristotle's, and its failure led to its being discarded. While the Copernican revolution did not tell us whether the atomists had been right about life, it did clarify that the moon and the planets are other worlds, not mere lights in the sky. That fact makes it plausible to imagine life elsewhere, even if we still do not have the information to conclude whether such life exists. The story of how our ancestors gradually figured out the basic architecture of the cosmos exhibits many features of what we now consider good science. For instance, our ancestors formulated and tested models against observations, modifying or replacing them if they failed those tests. The story also illustrates some classic mistakes, such as the absence of anyone before Kepler to question the belief that orbits must be circles. The ultimate success of the Copernican revolution led scientists, philosophers, and theologians to reassess the various modes of thinking that played a role in the 2,000-year process of discovering Earth's universe. Now, let's examine the principles of modern science that emerged from the lessons learned in the Copernican revolution. How can we distinguish science from non-science? It turns out to be quite difficult to define the term science precisely. The word comes from the Latin scientia, meaning knowledge. Not all knowledge is science, for example. You might know what music you prefer most, but your musical taste does not stem from scientific study. Science is difficult to define because not all science works similarly. For instance, you have heard that science follows a process known as the scientific method. An illustration of this method in its most idealized form. Consider what you would do if your flashlight suddenly stopped working. In hopes of fixing your flashlight, you might hypothesize that the batteries have died. In other words, you have a tentative explanation, or hypothesis, for the flashlight. A hypothesis is sometimes called an educated guess, and in this case the term educated refers to your prior knowledge that lights require batteries for operation. A simple prediction. If you replace the batteries with new ones, the flashlight should function properly. You can test this prediction by replacing the batteries. If the flashlight now works, you have confirmed your hypothesis. Unless it does, you must revise or discard your hypothesis, usually favoring one you can test, such as the bulb being burned out. The scientific method can be a useful idealization, but real science rarely progresses in such an orderly manner. Scientific progress sometimes occurs when an individual goes out and observes nature in a general way, hoping to learn something new and unexpected rather than conducting a careful set of experiments. This was the case with Galileo, who was not looking for anything in particular when he pointed his telescope at the sky and made his first startling discoveries. We still often approach science this way today, for example, when we build new telescopes or send missions to other worlds. When we sent them flying past Jupiter, the Voyager 1 and 2 spacecraft would find evidence of a subsurface ocean on Europa. We sent them to explore unknown areas and gain valuable scientific knowledge. Another case in which we cannot use the idealized scientific method comes with attempts to understand past events, such as the history of Earth or the origin and evolution of life on Earth. We cannot repeat or vary the past, so we must instead rely on careful study of evidence behind past events. For example, we learn about early life on Earth, not by observing it directly, but by piecing together its story from examining fossils and other evidence that we can find today. Nevertheless, we can still apply at least some elements of the scientific method. For example, when scientists first proposed that a massive impact may have been responsible for the death of the dinosaurs, they could predict some of the other types of evidence that should exist if their hypothesis was correct. Scientists made plans to make observations that might find evidence, and when they did, such as discovering an impact crater that was the appropriate age, it significantly strengthened the case for the impact hypothesis. A further complication in describing how science works is that scientists are human beings, so their intuitions and personal beliefs inevitably influence their work. He adopted the idea that Earth orbits the Sun, not because he had carefully tested it, but because he believed it made more sense than the prevailing view of an Earth-centered universe. As we have seen, his intuition guided him to the correct general idea. But he made specific errors due to his adherence to Plato's belief that heavenly motion must follow perfect circles. Considering the different methods to approach science, how can we determine what is scientific and what is not? To answer this question, we must examine the distinguishing characteristics of scientific thinking more closely. One way to define scientific thinking is to list the criteria that scientists use when they judge competing models of nature. Historians and philosophers of science have examined, and continue to examine, this issue in great depth, and various experts express somewhat different viewpoints on the details. Nevertheless, everything we now consider to be science shares the following three basic characteristics that we will refer to as the hallmarks of science. Modern science seeks explanations for observed phenomena that rely solely on natural causes. Science progresses through creating and testing models of nature that explain the observations as simply as possible. A scientific model must make testable predictions about natural phenomena that would compel us to revise or abandon the model if the predictions do not align with observations. Each of these hallmarks is evident in the story of the Copernican revolution. It demonstrates how Tycho's very careful measurements of planetary motion inspired Kepler to provide a clearer explanation of those motions. The comparison and testing of several competing models, particularly those of Ptolemaious and Kepler, clearly demonstrate the second point. We see the third in that each model could make precise predictions about the future motions of the Sun, Moon, planets, and stars in our sky. The failure of a model's model led to its modification or eventual discard. Kepler's model gained widespread acceptance due to its superior predictions compared to the Ptolemaic model, which better matched Tycho's observations. Remember that the original model of Copernicus did not match the data noticeably better than that of Ptolemy. Ptolemy scientists had judged Copernicus precisely on the accuracy of its predictions. They might have rejected it immediately. However, numerous scientists found elements of the Copernican model appealing, such as the simplicity of its explanation for apparent retrograde motion. They therefore kept the model alive until Kepler discovered a way to make it function. In fact, if agreement with data were the only criterion for judgment, we could imagine a modern-day Ptolemy adding millions or billions of additional circles to the geocentric model to enhance its alignment with observations. A sufficiently complex geocentric model could, in principle, reproduce the observations with almost perfect accuracy. But it still would not convince us that Earth is the center of the universe. We would still choose the Copernican view over the geocentric view because its predictions would be just as accurate. Yet, they would follow a much simpler model of nature. Occam's razor, named after the medieval scholar William Occam, suggests that scientists should prefer the simpler two models that agree equally well with observations. The third hallmark of science compels us to confront what constitutes a valid observation for testing predictions. Consider the claim that aliens are visiting Earth in UFOs. Proponents of this claim say that many thousands of eyewitness observations of UFO encounters provide evidence that it is true. But should these personal testimonials count as scientific evidence? The answer may not be obvious because all scientific studies involve eyewitness accounts on some level. For example, only a few scientists have personally made detailed tests of Einstein's relativity, and their reports of the results have convinced other scientists of the theory's validity. However, there's a difference between personal testimony about a scientific test and an observation of a UFO. The first can be verified by anyone, at least in principle, while the second cannot. Understanding this difference is crucial to grasping what counts as science and what does not. Even though you may never have tested Einstein's relativity, nothing stops you from doing so. To conduct the test, you may need several years of study, but you can confirm the results of other scientists. In other words, while you may currently be trusting the eyewitness testimony of scientists, you can always verify theirs for yourself. In contrast, there is no way for you to verify someone's account of a UFO. You cannot evaluate the UFO without clear photos or pieces. And in those cases where hard evidence for UFO sightings has been presented, a scientific study has never yet found the evidence to be strong enough to support the claim of alien spacecraft. Moreover, scientific studies of eyewitness testimony show it to be notoriously unreliable. For instance, eyewitnesses frequently disagree on what they observe after an event. As time passes, memories of the event may change more and more. When comparing memory to reality, individuals have occasionally reported vivid memories of events that never took place. This explains why many of us have argued with friends about who did what at what time. Since neither party can be certain, one of us is likely experiencing a false memory. Due to its proven unreliability, eyewitness testimony alone should never be utilized as scientific evidence, regardless of who reports it or how many individuals provide similar accounts. Evidence can only support a scientific model if it is independently verifiable and easily accessible for examination. For much the same reason, eyewitness testimony alone is usually insufficient for a conviction in criminal court. Additional evidence is required. It is important to realize that science is not the sole method to seek knowledge. For example, suppose you are shopping for a car, learning to play drums, or pondering the meaning of life. You may observe, exercise logic, and test hypotheses in each instance. However, these endeavors are undoubtedly not scientific, as they do not aim to create verifiable explanations or analyze observed natural phenomena. As long as non-scientific searches for knowledge make no claims about how the natural world works, they do not connect with science. In other words, just because something is not science does not mean it is incorrect. However, you will often hear claims about the natural world that seem to be based on observational evidence, but do not treat it in a truly scientific manner. Such claims are often called pseudoscience, which means false science. To distinguish real science from pseudoscience, a good first step is to check whether a particular claim exhibits all three hallmarks of science. Consider the example of individuals who assert a psychic ability to see the future and use it to make specific testable predictions. In this sense, seeing the future sounds scientific because we can test it. However, numerous studies have examined the predictions of seers and founts and found that they come true no more often than expected by pure chance. If the seers were scientific, they would admit that this evidence undercuts their claim of psychic abilities. Instead, they generally make excuses, such as saying that the predictions didn't come true because of some psychic interference. King makes testable claims, but disregarding the test results tarnishes his claimed ability to predict the future. The idea that science is objective, meaning that all people should be able to find the same results, is important to the validity of science as a means of seeking knowledge. However, there is a difference between science's overall objectivity and individual scientists' objectivity. In particular, because science is practiced by humans, individual scientists bring their personal biases and beliefs to their scientific work. Personal bias can influence the way a scientist proposes or tests a model. For example, many scientists choose their research projects based on personal interests, rather than on some objective formula. In some extreme cases, scientists have even been known to cheat deliberately or subconsciously to obtain the desired result. For example, consider Percival Lowell's mapping of artificial canals on Mars. Because no such canals exist, he must have allowed his beliefs about extraterrestrial life to influence the way he interpreted blurry telescopic images. In essence, a form of cheating, though not intentional. Bias can sometimes show up even in the scientific community as a whole. Any scientist may not consider some valid ideas because they fall too far outside the general thought patterns or paradigms of the time. Einstein's relativity provides an example. Many scientists in the decades before Einstein had gleaned hints of the theory, but did not investigate them, at least partly because the ideas seemed too outlandish. The beauty of science is that it encourages continued testing by many individuals. Even if personal biases affect some results, tests by others should eventually uncover the mistakes. Similarly, if a new idea is correct but falls outside the accepted paradigm, sufficient testing and verification of the idea should eventually force a change in the paradigm. In this sense, science ultimately serves as a tool for reaching consensus, particularly on scientifically studied topics. What is a scientific theory? The most successful scientific models explain a wide variety of observations regarding just a few general principles. When a powerful yet simple model makes predictions that survive repeated and varied testing, scientists elevate its status and call it a theory. Some famous examples are Isaac Newton's gravity, Charles Darwin's evolution, and Albert Einstein's relativity. The scientific meaning of the word theory is quite different from its everyday meaning, in which we equate a theory more closely with speculation or a hypothesis. In everyday life, someone might get a new idea and say, for example, "I have a new theory about why people enjoy the beach." Without the support of a broad range of evidence that others have tested and confirmed, this theory is merely a conjecture. In contrast, Newton's gravity qualifies as a scientific theory because it uses simple physical principles to explain numerous observations and experiments. Despite its success in explaining observed phenomena, a scientific theory can never be proven true beyond all doubt, because ever more sophisticated observations may eventually disagree with its predictions. However, a large, compelling body of evidence must support anything that qualifies as a scientific theory. In this sense, a scientific theory is unlike a hypothesis or any other guess. A hypothesis that has not yet been thoroughly tested is subject to change at any time. In contrast, we can discard or replace a scientific theory only if we possess a superior method of explaining the evidence that supports it. Once more, the theories of Newton and Einstein provide outstanding examples. A vast body of evidence supports Newton's gravity, but by the late 19th century, scientists had discovered cases where its predictions did not perfectly match observations. Only when Einstein developed his general theory of relativity in the early 20th century, which could match the observations, did these discrepancies find an explanation. Yet Newton's numerous successes should not be overlooked, and Einstein should not have been accepted if he could not explain them adequately. It did, which is why we now view Einstein's theory of gravity as broader than Newton's. We will discuss Newton's theory in the next section, but some scientists today strive to develop a theory of gravity surpassing Einstein's. If Einstein's new theory ever gains acceptance, it must match all the successes of Einstein's work in new realms, where Einstein is not present. We have compiled an overview of the nature of modern science and its historical development. We have the general process by which science advances, a process crucial to all sciences but particularly important in astrobiology, where, for instance, widespread belief in aliens sometimes makes it difficult to separate fact from fiction. Due to its significance, we will persist in emphasizing the process of science throughout the book. Additionally, in the final first sections of each chapter, we will delve deeper into a specific topic to display science in action. In this chapter, we focus on gravity. Gravity is clearly important to life in the universe. On a simple level, life would float right off its planet without gravity. On a deeper level, stars and planets could never have been born in the first place without gravity. So we presume that life could not start in a universe where gravity was absent or worked significantly differently than in our universe. Even more important to our purposes, gravity provides a powerful illustration of the sometimes surprising distinction scientists make between facts and theories. Gravity is clearly a fact. Things fall when you drop them, and planets orbit the sun. However, scientifically, gravity is also a theory because we use detailed mathematical models of gravity to explain why things fall down and why planets orbit. Gravity is not unique in this way. For example, scientists make the same distinction when they talk about atoms being real and the atomic theory used to explain them, and when they talk about whether evolution truly occurred and the theory used to explain it. We can gain deeper insight into how words often carry dual meanings by exploring how gravity models have evolved. What is gravity? The true nature of gravity has never changed, but human ideas about it have evolved. In ancient Greece, Aristotle imagined gravity as an inherent property of heavy objects. For example, he claimed that earth and water had gravity, which made them fall toward our central world, while air and fire had levity, which made them rise up. Aristotle successfully explained a few observed facts, such as that rocks fall to the ground, but he didn't read any specific predictions, such as how long it would take a rock to reach the ground if dropped from a tall cliff. Still, no one developed a much better idea for nearly 2,000 years. The first real breakthrough in human understanding of gravity came in 1666, when Newton, by his own account, saw an apple fall to Earth, and suddenly realized that the gravity making the apple fall was the same force that held the moon in orbit around Earth. He soon worked out a mathematical model to explain his observations, but it didn't result widely until 1687, when he published Principia. The universal law of gravitation tells us the strength of the gravitational attraction between the two objects. Newton mathematically expressed the force of gravity with his universal law of gravitation. 3 simple statements summarize this law. Every mass attracts every other mass through the force called gravity. The gravitational force attracting any two objects is directly proportional to the product of their masses. For instance, when you double the mass of one object, you double the force of gravity between the two objects. The gravity between two objects decreases with the square of the distance between their centers. That is, the gravitational force follows an inverse square law with distance. For example, doubling the distance between two objects weakens the force of gravity by a factor of 2 squared or 4. These 3 statements convey all that we need to understand regarding Newton's law of gravitation. Newton showed that this law explained many facts that other scientists had already discovered. For example, he showed that, when combined with his laws of motion, the universal law of gravitation explained the orbits of all the planets around the Sun, including Kepler's and Earth, as well as the orbit of the Moon around Earth. He also demonstrated that it explained Galileo's theory that, absent air resistance, all objects fall to the ground at the same rate, regardless of their mass. Soon thereafter, Sir Edmund Halley, who lived from 1656 to 1742, used the law to calculate the orbit of a comet seen in 1682. His calculations showed that the comet would return in 1758. Halley's comet followed him despite his untimely death and returned precisely on schedule. Many 18th century scientists believed they had solved the mystery of gravity due to these and other successes of Newton's law of gravitation. However, a problem arose a few decades after the 1781 discovery of the planet Uranus. Observations of Uranus showed its orbit to be slightly inconsistent with the expected orbit. According to Newton, scientists wondered if Newton's gravity might not be as exact as they had imagined. However, in the summer of 1846, French astronomer Urbain Le Verrier suggested that the inconsistency could be explained by a previously unseen 8th planet orbiting the Sun beyond Uranus. He used Newton's law of gravitation to predict where the planet must be in the sky. He sent a letter to Johann Galle of the Berlin Observatory, suggesting a search for the 8th planet. On the night of September 23, 1846, Galle pointed his telescope to the position suggested by Leverrier. There, within 1 degree of its predicted position, he saw the planet Neptune. It was a stunning triumph for Newton, which gave scientists far more confidence that the law of gravity was truly universal. Today, we can see Newton's law of gravitation in action throughout the universe. In the orbits of extrasolar planets around their stars, stars around the Milky Way galaxy, and galaxies in orbit around each other. There seems to be no reason to doubt the universality of the law. However, we also now know that Newton's law does not tell the entire story of gravity. Moreover, while Newton's is a useful description of how gravity works, it still doesn't say what it is. Do we truly understand gravity? Not long after Leverrier predicted Neptune's existence, astronomers discovered another slight discrepancy between a planetary orbit and the prediction made with Newton's gravity. This time, it involved the planet Mercury. Leverrier again set to work on the problem, suggesting it might be solved if there were yet another unseen planet, this one orbiting the Sun closer than Mercury. He even gave it a name, Vulcan. But searches showed no sign of this planet, and we now know it does not exist. So why was there a discrepancy in Mercury's orbit? Albert Einstein, born in 1879 and passing in 1955, provided the answer when he published his general theory of relativity in 1915. To understand what Einstein did, we must look more deeply at Newton's law of gravity. According to Newton's theorem, every mass exerts a gravitational attraction on every other mass, no matter how far away it is. Upon reflection, action at a distance appears somewhat enigmatic. For instance, how does Earth perceive the attraction of the Sun and determine its orbit? Newton himself was troubled by this idea. A few years after publishing his law of gravity in 1687, Newton wrote that one body may act upon another at a distance through a vacuum, and force may be conveyed from one to another, is so absurd that I believe no man with a competent thinking faculty can ever fall into it. This type of absurdity was true to Einstein, whose scientific career can, in many ways, be viewed as a quest to find simple principles underlying mysterious laws. Although we will not go into the details, Einstein discovered that he could explain the mysterious action at a distance by assuming that all objects reside in four-dimensional spacetime. Massive objects curve this spacetime, and other objects follow the curvature, much like marbles following the contours of a bowl. Figure 2.17 uses a two-dimensional analogy to illustrate the idea, showing how planetary orbits are the straightest paths allowed by the structure of spacetime near the Sun. Einstein removed the mystery of action at a distance by telling us that gravity arises from how masses affect the universe's basic structure. In other words, he told us that gravity is the curvature of spacetime. When Einstein worked out the mathematical details of his theory, he found that it gave almost precisely the same answers as Newton's. Newton's law of gravitation yields similar results for relatively weak sources of gravity. But when gravity intensifies, the results significantly differ. Thus, he obtained essentially the same results as Newton for planets orbiting far from the Sun, where the effects of the Sun's gravity are weaker. They are weaker. Suns are weaker. But a slightly different answer for Mercury, where the effects of the Sun's gravity are far stronger. Einstein stretched the observed orbit of Mercury, giving him confidence that he had discovered an underlying truth about the nature of gravity. Keep in mind that Einstein did not prove that Newton was not correct. After all, Newton's law had already proved valid in numerous situations throughout the universe. Instead, he demonstrated that Newton's theory only approximates a more precise theory of gravity, the general theory of relativity. Under most circumstances, the approximations are so good that we can hardly tell the difference between the two ways of viewing gravity. Still, in cases of strong gravity, and the works of Einstein and Newton in the past century, scientists have had ample opportunity to test Einstein's rough observations of the distant cosmos and experimental tests in laboratories and orbiting spacecraft. Thus far, it has successfully passed every test. So, does that mean we truly understand gravity today? Most scientists doubt it because there is at least one known hole in INST. According to general relativity, the curvature of spacetime must become infinitely great when gravity becomes infinitely strong, as it would at the centers of the objects known as black holes. However, another scientific theory, also well tested, gives a very different answer for what should happen in such places. The theory of quantum mechanics, which successfully explains the workings of atoms, gives an answer that directly contradicts the answer given by relativity. Scientists are working hard to reconcile this discrepancy between two otherwise successful theories, but no one knows how it will turn out. In summary, Einstein's theory of relativity, a successful theory of gravity, functions throughout the universe. Newton's universal law of gravitation is now considered an approximation to Einstein's. However, our understanding of gravity remains incomplete. And until we address the existing gaps in Einstein's, we cannot anticipate. Studying life in the universe brings together many different research fields, each contributing to different aspects of our understanding. Biology helps us understand life's nature so we know what we seek. Chemistry and biochemistry help us understand how life works and how it might have arisen in the first place. Planetary science, which includes geology and atmospheric science, helps us understand the conditions that might allow life to arise and survive on other worlds. Physics teaches us about the fundamental laws of nature that both enable and constrain the possibilities for life elsewhere. That is why we will study aspects of these sciences as we continue our survey of astrobiology in this documentary. The universe is the canvas on which all these sciences come together. So to gain a true appreciation of the scientific search for life, we first need to discuss fundamental concepts of the universe itself. In this section, we'll explore the modern understanding of the overall nature of the universe, the current theory about how planets are born, and the basic properties of the matter and energy that make up all living things. We saw how and why people long assumed that Earth was at the center of the universe, and that the sun, moon, planets, and stars belonged to an entirely separate realm known as the heavens. This Earth-centered, geocentric view of the universe gave our planet a unique place in the cosmos, and implied a clear distinction between Earth and any place else. Although the geocentric belief did not prevent people from speculating about inhabitants of the heavens, recall the debate between the atomists and the Aristotelians, it certainly limited the possibilities. The possibilities changed dramatically with the Copernican revolution, when Earth finally lost its central place through the work of Copernicus, Tycho Brahe, Kepler, and Galileo. This new view of Earth's place in the universe, which gained acceptance only about 400 years ago, showed that other planets are other worlds, not just wandering night skylights. The realization that the sun is a star added even more possibilities because it became reasonable to imagine planets around other stars. We still do not know whether any other planet has life in our solar system or elsewhere. However, we have learned much about the universe in the past 400 years, including its size, content, and history. As discussed in this section, these new discoveries have given us good reason to think it's worth some scientific effort to search for life beyond Earth. What major lessons does modern astronomy teach us about our place in the universe? The origin of astronomy is unknown, but it has focused on sky objects for most of human history. These observations were enough to meet immediate practical needs, such as telling the time and the seasons from the sun's path through the sky, or predicting the tides from the position and phase of the moon. When the Greeks began their attempts to explain the observed motions by seeking to understand the architecture of the cosmos, the human realm of astronomy expanded. This effort culminated some 2,000 years later when Kepler finally described the laws by which the planets orbit the sun. However, science had advanced only far enough to say how the planets move around the sun, not why they move, as they do. The key change in human understanding that allowed the emphasis to shift from how to both how and why occurred when Newton discovered that the planets are held in their orbits about the sun by the same force of gravity that makes an apple fall to Earth. With this discovery, Newton delivered the final, shattering blow to the Aristotelian conception that Earth must, by necessity, be unique. The heavens could no longer be considered separate realms made from different materials, the ether or quintessence, and operated under laws different from Earth's. Newton ended the ancient distinction between Earth and the heavens finally making it possible to think of both as part of one universe. The modern science of astronomy begins where Newton left off, as we seek to use his and other discoveries about the laws of nature to understand the history and workings of the objects we see in the sky. Today, powerful telescopes enable us to study objects whose existence was not even contemplated in Newton's time. And experimental techniques allow us to probe the inner workings of the cosmos at a level far deeper than Newton probably could have imagined. Almost everything we have learned through modern astronomy has at least some importance to studying life in the universe. For our purposes in this documentary, however, three ideas are especially important in framing the universal context for everything else we will study. The universe is vast and old. Its vastness implies an enormous number of worlds in which life may exist. And its old age means there has been plenty of time for life to begin and evolve. The elements of life are widespread. Observations show that the basic chemical elements that make up Earth and life exist throughout the universe. Thus, at minimum, the raw ingredients of life should be found in many other worlds. The same physical laws on Earth operate throughout the universe. Every experiment and observation made to date has supported Newton's conclusion that the laws of nature are the same everywhere. In that case, it is reasonable to think that the same processes that made life possible on Earth have also made existence possible on other worlds. Together, these ideas reinforce the primary lesson of the Copernican revolution. We are not the center of the universe. Our planet may be special to us, but it is just one planet orbiting one rather average star in a universe home to many similar stars and likely to many similar planets. The seemingly ordinary nature of our circumstances significantly contributes to the plausibility of imagining a universe teeming with life. The structure, scale, and history of the universe. We will devote the rest of this section to understanding the three important ideas on the previous page. They are all interrelated, so we cannot simply go through time. Instead, we'll focus on key features of the universe as we understand it today so that you can see how the major ideas emerge from this modern picture. What does modern science tell us about the structure of the universe? Let's begin our brief survey of the universe by examining the current state of knowledge about its general makeup, our cosmic address. Earth is a planet in our solar system which consists of the Sun and all the objects that orbit it. The planets and their moons and countless smaller objects, including rocky asteroids and icy comets. Our Sun is a star, just like the stars in our night sky. Only a small portion of the Milky Way galaxy, a vast disc-shaped collection of stars, includes the Sun and all the stars we can see with our naked eyes. A galaxy is a huge island of stars in space, containing a few 100 million to a trillion or more stars. The Milky Way galaxy is relatively large, containing over 100 billion stars. Our solar system is located about halfway out through the disk of the galaxy, where it orbits the galactic center once every 230 million years. Space is home to billions of other galaxies, most of which cluster together. Our Milky Way, for example, is one of the two largest among about 40 galaxies in the local group. Groups of galaxies with more than a few dozen members are often called galaxy clusters. On a large scale, observations show galaxies and galaxy clusters arranged in giant chains and sheets with huge voids between them. The regions in which galaxies and galaxy clusters are most tightly packed are called superclusters, essentially clusters of galaxy clusters. Our local group is located on the outskirts of the local supercluster. Together, all these structures make up our universe. In other words, the universe is the sum of all matter and energy, encompassing the superclusters, voids, and everything within them. The scale of the solar system. While it's easy to list the levels of structure shown in Figure 3.1, it takes additional thought to comprehend the vast scales involved. Let's begin by considering the scale of our own solar system. Illustrations and photo montages often make our solar system look crowded with planets and moons. But the reality is far different. One of the best ways to develop a perspective on cosmic sizes and distances is to imagine our solar system shrunk down to a scale on which you could walk through it. The Voyage Scale Model solar system in Washington, D.C. makes such a walk possible. The Voyage model shows the Sun, the planets, and the distances between them, at 1/10 billionth of their actual sizes and distances. The Voyage scale displays the Sun and planets at their correct sizes, but not their distances. The model Sun is the size of a large grapefruit, Jupiter is the size of a marble, and Earth is the size of the ballpoint in a pen. You can immediately see some key facts about our solar system. For example, the Sun is far larger than any of the planets, which vary considerably in size. The storm on Jupiter, known as the Great Red Spot, visible near Jupiter's lower left in the painting, has the potential to swallow up the entire Earth. The scale of the solar system becomes even more remarkable when you combine the sizes shown in Figure 3.3a with the distances illustrated by the map of the Voyage model in Figure 3.3b. For example, the ballpoint-size Earth is about 15 meters, 16.5 yards, from the grapefruit-size Sun, which means you can picture Earth's orbit by imagining a ballpoint taking a year to circle with a radius of 15 meters around a grapefruit. The most striking feature of our solar system when we view it to scale is its emptiness. The Voyage model shows the planets along a straight path. So we'd need to draw each planet's orbit around the model's Sun to show the full extent of our planetary system. Fitting all these orbit bits would require an area measuring more than a kilometer on a side, an area equivalent to more than 300 football fields arranged in a grid. Spread over this large area, only the grapefruit-sized Sun, the planets, and a few moons would be big enough to notice with your eyes. The rest would look virtually empty. That's why we call it space. Seeing the solar system in scale can help us understand why the search for life is only beginning. The Moon, the only other world humans have ever stepped on, lies about 4 centimeters, an inch and a half, away from Earth in the model. On this scale, the palm of your hand can cover the entire universe region humans have so far traveled. Our robotic spacecraft have traveled much farther, but these journeys are long and difficult. For example, the trip to Mars is some 200 times as far as the trip to the Moon. And while you can walk from the Sun to Pluto in a few minutes on the Voyage scale, the New Horizons spacecraft that is currently making the real journey, launched January 2006, will have been in space nearly a decade by the time it finally flies past Pluto. Distances to the stars. If you visit the Voyage model in Washington, D.C., you can walk roughly 600 meters from the Sun to Pluto in just a few minutes. But how far would you walk to reach the next star on this scale? Amazingly, you would need to walk to California. If this answer seems hard to believe, you can check it yourself. We usually measure the distances to stars in units of light years. 1 light year is the distance that light can travel in 1 year, which is about 10 trillion kilometers, see Cosmic Calculations 3.1. On the 1 to 10 billion Voyage scale, a light year becomes about 1,000 kilometers, because 10 trillion divided by 10 billion equals 1,000. The nearest star system to our own, a 3-star system called Alpha Centauri, is about 4.4 light-years away. This distance becomes about 4,400 kilometers, 2,700 miles, on the 1 to 10 billion scale, or roughly equivalent to the distance across the United States. The tremendous distances to the stars give us some perspective on the technological challenge of searching for life in other star systems. For example, because the largest star of the Alpha Centauri system is roughly the same size and brightness as our Sun, viewing it in the night sky is somewhat like being in Washington, D.C. and seeing a bright grapefruit in San Francisco, neglecting the problems introduced by the curvature of Earth. It may seem amazing that we can see this star at all, but the blackness of the night sky allows the naked eye to see it as a faint dot of light. Now consider the difficulty of detecting planets orbiting nearby stars. It is equivalent to looking from Washington, D.C. and trying to see ballpoints or marbles orbiting grapefruits in California or beyond. At least some of our technology can detect such planets, which is remarkable given this challenge. The vast distances to the stars offer a sobering lesson about interstellar travel, although science fiction shows and movies like Star Trek and Star Wars make such travel look easy. But the reality is far different. Consider the Voyager 2 spacecraft. Launched in 1977, Voyager 2 flew by Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Voyager 2 travels towards the stars at a speed of nearly 50,000 kilometers per hour, approximately 100 times faster than the speed of a bullet. Although it's not headed that way, Voyager 2 would take 100,000 years to reach Alpha Centauri at this speed. Clearly, convenient interstellar travel remains well beyond our present technology, if possible. The scale of the galaxy. We turn to the Milky Way galaxy, so vast that only a handful of its more than 100 billion stars could even fit on Earth with the 1 to 10 billion scale. To picture the galaxy, let's reduce our solar system scale by another factor of 1 billion, making it a scale of 1 to 119. On this new scale, each light year becomes 1 millimeter, and the 100,000 light-year diameter of the Milky Way galaxy becomes 100 meters, or about the length of a football field. Visualize a football field with a scale model of our galaxy centered over midfield. Imagine our entire solar system as a tiny dot centered around the 20-yard line, corresponding to our actual distance of approximately 27,000 light-years from the galaxy's center. The 4.4 light-year separation between our solar system and Alpha Centauri becomes just 4.4 millimeters on this scale, smaller than the width of your little finger. If you stood at the position of our solar system in this model, millions of star systems would lie within reach of your arms. Consider light travel times as another method to gauge the galaxy's size. Light travels extremely fast by earthly standards. If you could circle Earth at the speed of light of 300,000 kilometers per second, you could complete almost 8 circuits in just 1 second. But despite this awesome speed, light requires years to cross the vast chasms between the stars. That is why we measure interstellar distances in light years. For example, when we say that Alpha Centauri is 4.4 light-years away, we mean that its light takes 4.4 years to reach us. This fact has an astonishing implication. We cannot see what Alpha Centauri looks like today, but can see only what it looked like 4.4 years ago, when the light now reaching our eyes, and telescopes first left on its journey. It also has an important implication for the possibility of conversing with any beings who might happen to live in the Alpha Centauri system. We generally transmit messages over long distances with radio waves, a form of light that travels at the speed of light. If we sent a radio message to Alpha Centauri, the message would take 4.4 years to get there, and any reply would take the same 4.4 years to travel to us. You'd need a lot of patience for a conversation, which would be almost 9 years from when you said, "Hello, how are you?" until you heard the reply, "Fine, thanks, and you?" The effect becomes more dramatic at greater distances. Consider the Orion Nebula, a giant cloud of gas and dust, meaning tiny solid particles, in which new stars and planets are being born. The Orion Nebula lies about 1,500 light-years away. Thus, we see the Orion Nebula as it looked about 1,500 years ago, about the time of the fall of the Roman Empire. To receive a radio message from aliens in the Orion Nebula, we must send it approximately 1,500 years ago. If we sent a message in return, we couldn't expect to hear a reply for at least 3,000 years. The Orion Nebula is still quite near relative to the scale of the galaxy. Using our football field-size scale model, the nebula lies only about 1.5 meters from Earth. It takes light 100,000 years to cross the 100,000 light-year diameter of the Milky Way galaxy. Given that we are located about 27,000 light-years from the galactic center, a signal now reaching us from the far outer edge of the galaxy would have been sent more than 70,000 years ago. The search for extraterrestrial intelligence, or SETI, which listens for signals from alien civilizations, is, in essence, a search to hear from civilizations that used radio technology some decades, centuries, or millennia in the past. The number of star systems in the Milky Way galaxy is no less remarkable than its size. Imagine that you are having difficulty falling asleep at night, perhaps because you are contemplating the vastness of our galaxy. You choose to count stars instead of sheep. The Milky Way has over 100 billion stars, perhaps as many as 1 trillion. Averaging 1 star per second, how long would it take to count 100 billion stars? The answer is 100 billion seconds. But how long is that? You can get the answer by dividing 100 billion seconds by 60 seconds per minute, 60 minutes per hour, 24 hours per day, and 365 days per year. If you do this calculation, you'll find that 100 billion seconds is over 3,000 years. In other words, you would need thousands of years to count the stars in the Milky Way galaxy, let alone study them or search their planets for signs of life. And this assumes you never take a break. No sleeping, no eating, and no dying. The contents of the universe. The Milky Way galaxy is just one of billions of galaxies in the universe, and we'll discuss the overall extent of the universe shortly. First, however, it's worth briefly discussing the universe's content. We've said that the universe is the sum of all matter and energy. But what exactly is this? Until a few decades ago, astronomers assumed that the universe's matter was primarily found in stars and galaxies, while the universe's energy took the form of light. Now, this visible matter and energy appear merely on the surface of a more mysterious universe. Just as planets orbit the Sun, stars orbit the center of the Milky Way galaxy. The more massive the galaxy, the stronger its gravity and the faster stars should be orbiting. By carefully studying stellar orbits, astronomers have created a map of matter distribution in the Milky Way. The surprising result is that while most of the matter we see consists of stars and gas clouds in the galaxy's relatively flat disk, most of the mass lies unseen in a much larger spherical halo surrounding the disk. Figure 3.5. The halo's unseen mass is called dark matter because we haven't detected any light from it, but we have detected its gravitational effects. Research on other galaxies indicates that dark matter constitutes most of their composition. In fact, most of the mass in the universe seems to be made of this mysterious dark matter, which means that its gravity must have played a key role in assembling galaxies. Evidence of the existence of dark matter has been building for several decades. More recently, scientists have gathered evidence of an even greater mystery. The universe seems to contain a mysterious form of energy, nicknamed dark energy by analogy to dark matter, pushing galaxies apart even while their gravity tries to draw them together. As with dark matter, scientists have good reason to think that dark energy exists but lack any real understanding of its nature. In recent years, scientists have conducted a census of the matter and energy in the universe. The results show that dark energy and dark matter are by far the main ingredients of the universe. The ordinary matter, atoms and molecules, that makes up stars, planets, and life, apparently represents only a few % of all the matter and energy in the universe. They appear to be the dominant constituents of the universe, but we don't know much about them. Dark matter and dark energy are arguably the biggest mysteries in astronomy today. However, they do not appear to affect the general evolution of stars, planets, or life, so they seem unlikely to affect our study of life in the universe. Nevertheless, as we seek to answer questions about life elsewhere, the mysteries of dark matter and energy should remind us that nature may still hold surprises that no one has foreseen. What does modern science tell us about the history of the universe? We have surveyed the structure and scale of our vast universe, finding that Earth seems to hold a rather ordinary place. Modern understanding of the universe's history further reinforces the idea that we live in a world that ought to be similar to many others, giving us additional reason to think that life might exist elsewhere. Our cosmic origins. Birth of the universe. The universe's expansion began with the hot and dense Big Bang. The cubes show how one region of the universe has expanded with time. The universe continues to expand, but gravity has pulled matter together on smaller scales to make galaxies. Galaxies as cosmic recycling plants. The early universe contained only two chemical elements, hydrogen and helium. Stars created all other elements, recycling them from one stellar generation to the next within galaxies like our Milky Way. Earth and life. By the time our solar system was born 4.5 billion years ago, about 2% of the original hydrogen and helium had been converted into heavier elements. We are, therefore, star stuff, because we and our planet are made from elements manufactured in stars that lived and died long ago. Telescopic observations of distant galaxies show that the universe is expanding, meaning that average distances between galaxies increase with time. This fact implies that galaxies must have been closer together in the past. And if we go back far enough, we must reach the point at which the expansion began. We call this beginning the Big Bang. And based on the observed rate of expansion, we estimate that it occurred about 14 billion years ago. The three cubes in the upper left corner represent the expansion of a small piece of the universe over time. Two key lines of evidence support the idea that the universe began in the Big Bang. First, we have detected radiation left over from the Big Bang. Just as compressing gas inside a car engine, the piston compresses gas in a cylinder, makes the gas much hotter and denser. The universe must have been much hotter and denser if it had been smaller in the past. Thus, if the Big Bang had occurred, the universe would have begun with its matter compressed to extremely high temperatures and density, producing intensely bright radiation, light. Calculations show that, as the universe expanded and cooled with time, it should have left behind a faint glow of radiation we could detect with radio telescopes. This radiation, known as the cosmic microwave background, has been detected and studied. Its characteristics, such as its spectrum and distribution, precisely match the characteristics expected if it is the leftover radiation from the Big Bang, providing strong support for the idea that the Big Bang happened about 14 billion years ago. The second line of evidence comes from the overall chemical composition of the universe. Calculations that run the expansion backward allow scientists to predict exactly when and how chemical elements should have been born in the early universe. The calculations clearly predict that if the Big Bang occurred, then the chemical composition of the universe should be about 3/4 hydrogen and 1/4 helium by mass. Observations show that this is indeed a close match to the overall chemical composition of the universe. This excellent agreement between prediction and observation strongly supports the Big Bang theory. Note also that the prediction means the universe was born without elements heavier than hydrogen and helium, except a trace of lithium, which means the early universe lacked the elements that make life on Earth. We'll discuss these elements shortly. The universe has continued to expand since the Big Bang, but on smaller scales, the force of gravity has drawn matter together. Structures such as galaxies and clusters of galaxies occupy regions where gravity has won out against the overall expansion. While the universe continues to expand, individual galaxies and galaxy clusters do not expand. The three cubes in the figure also illustrate this idea. Notice that as the region grows, the matter within it has clumped into galaxies and clusters. Most galaxies, including our Milky Way, formed within 1 billion years after the Big Bang. Stellar lives and galactic recycling. Hubble's original measurements of the universal expansion were fairly crude, but they have been greatly improved since then. Today, we know the expansion rate is within a few percent, and we even have measurements that show roughly how it has changed with time. Knowing a car's speed and current distance from home can allow you to determine how long it's been since the car left. Knowing the rate of expansion and the current separations of galaxies allows astronomers to determine how long it's been since the expansion began. The answer, about 14 billion years, must represent the universe's age. Measurements of the expansion rate are also responsible for one of the biggest mysteries in astronomy, the mystery of dark energy discussed briefly in this section. Gravity slows down a ball thrown upwards as it rises. Similarly, we would expect the mutual gravitational attraction of all the galaxies in the universe to slow the expansion rate with time. However, measurements show the opposite. The expansion rate has increased with time, at least for the past few billion years. This acceleration of expansion must be caused by the energy that can push galaxies apart. The concept of dark energy comes from there, though we don't know what it is. Planets may be born at the same time. In the same way that spinning a ball of dough causes it to spread out into a flat pizza, the natural spin of a contracting interstellar cloud keeps some of its gas spread away from its center, while shaping it into a flattened disk. The planets of our own solar system formed in such a disk, which is why they all ended up orbiting the Sun in nearly the same plane. Once a star is born, it shines with energy released by the nuclear fusion in its core. During most of a star's life, nuclear fusion combines hydrogen nuclei to make helium nuclei. It takes 4 hydrogen nuclei to make 1 helium nucleus. The process involves several steps. Energy is released because a helium nucleus has slightly less mass than the 4 hydrogen nuclei. This means that a small amount of the mass of the hydrogen has disappeared and become energy in accord with Einstein's famous formula, expressing the equivalence of matter and energy. E equals mc squared, where E is the energy, m is the mass, and c is the speed of light. Indeed, that is how our Sun shines today, with energy generated deep in its core by hydrogen fusion into helium. A star lives until it exhausts all its usable fuel for fusion. The rate at which a star burns through its fuel depends on its mass. More massive stars with much denser and hotter cores burn through their fuel at far greater rates than less massive stars. In essence, more massive stars have their engines running hotter and faster. This compensates for the fact that larger stars have more fuel to burn. The most massive stars live only a few million years. Stars, like our Sun, live 10 billion years. And lower mass stars can live hundreds of billions of years. In its final death throes, when its fuel for fusion has been exhausted, a star blows much of its content back into space. In particular, massive stars die in titanic explosions called supernovae, figure 3.8. The returned matter mixes with other matter floating between the stars in the galaxy, eventually becoming part of new clouds of gas and dust, from which new generations of stars can be born. Galaxies therefore function as cosmic recycling plants, reusing material expelled from dying stars to make new generations of stars and planets. There is a deeper connection between the recycling of stellar material and our existence. Recall that the Big Bang theory predicts that the universe should have been born containing only the simplest chemical elements: hydrogen and helium, and a trace of lithium. Other elements like carbon, nitrogen, oxygen, and iron primarily comprise living things and the Earth. Where did these elements come from? Evidence indicates that stars manufactured these elements. We cannot see inside stars, but we can use the laws of physics to predict what must happen under the high temperature and high density conditions in stellar cores. These calculations tell us that stars spend most of their lives generating energy by fusing hydrogen into helium. Toward the ends of their lives, stars like our Sun can fuse helium into carbon. Fusing 3 helium nuclei together makes 1 carbon nucleus. The Sun will stop the fusion process there, but the cores of more massive stars can continue to create many other heavy elements. For example, they can fuse carbon into oxygen and silicon, oxygen into neon and sulfur, and so on up to iron. Nuclear reactions accompanying stellar death can still produce other elements. All these manufactured elements then disperse into space after the star dies. At least 3 lines of observational evidence confirm this theoretical prediction. First, stars of different ages show the expected pattern in the proportions of elements heavier than helium that they contain. The oldest stars are made of nearly pure hydrogen and helium. Heavier elements make up less than 0.1% of their mass. Just as we would expect for objects born before there had been time for stars to make much else. Younger stars, like our Sun, were born with higher proportions, up to about 2%, of their mass in the form of elements heavier than hydrogen and helium, telling us that they were born from gas clouds that contained the elements manufactured and released by earlier generations of stars. The second line of evidence comes from studies of chemical elements' overall abundance in the universe today. The theory of nuclear fusion in massive stars makes specific predictions about relative abundances. For example, it says that carbon and oxygen elements should be more abundant than nitrogen, and that neon should be more abundant than fluorine. The observed relative abundances of the elements. Notice, for example, that nitrogen is less abundant than carbon and oxygen. In fact, detailed calculations predict a pattern of abundances that almost perfectly matches these observations, even including all the up and down wiggles that appear on the graph. The third line of evidence comes from studies of the gas from exploding stars, such as the Crab Nebula shown in Figure 3.8. Models of massive stars and their deaths allow astronomers to calculate the precise makeup expected for these clouds from recently deceased stars. And again, the observations match the predictions quite well. The importance of this stellar manufacturing should be clear. Without it, our universe would not contain the chemical elements we are made of. The recycling of matter and the production of heavier elements had already been taking place in the Milky Way galaxy for billions of years before the Sun and the planets were born. By then, stars had converted about 2% of the original hydrogen and helium into heavier elements. Thus, the cloud that gave birth to our solar system consisted of about 98% hydrogen and helium and 2% of everything else by mass. This 2% may sound small, but it was more than enough to make the small, rocky planets of our solar system, including Earth. On Earth, some of these elements became the raw ingredients of life, ultimately blossoming into the enormous diversity of life we see today. Most of our material came from dead stars before our Sun was born. As astronomer Carl Sagan, 1934 to 1996, said, "We are star stuff." The fact that we are made of star stuff has important implications for the possibility of finding life elsewhere in the universe. Stellar and galactic recycling processes operate throughout the Milky Way galaxy, and in every similar galaxy. So, we expect the chemical composition of many other star systems to be similar to ours. Observations confirm this expectation. While there is some variation in the precise proportions, in particular, stars that were born long ago have much lower proportions of heavy elements. The overall composition of our solar system is typical. We conclude that many, and perhaps even most, other star systems have the necessary raw materials to build Earth-like planets and life. The scale of time. When we discussed the universe's structure, we had to carefully consider scale to understand how greatly one level differs from the next. In much the same way, it's easy to state that the universe is 14 billion years old. But it requires deeper thought to begin grasping this age's truly astronomical meaning. You are probably familiar with using timelines to represent historical events. We'll use a slight variation on this theme, making a scale for a time in which we imagine compressing the universe's entire history, from the Big Bang to the present, into a single year. According to this cosmic calendar, the Big Bang occurs at the first instant of January 1st, and the present moment occurs at midnight on December 31st. For a universe about 14 billion years old, each month on the cosmic calendar represents a little more than 1 billion years, each day represents about 40 million years, and every second represents more than 400 years. On this scale, the Milky Way galaxy formed by early February, although it may not have immediately assumed its spiral shape. Many generations of stars lived and died in the subsequent cosmic months, enriching the galaxy with the star stuff from which we and our planet are made. Our solar system and planet did not form in real time until early September on this scale, or about 41 billion years ago. By late September, life on Earth was flourishing. However, for most of Earth's history, living organisms remained microscopic. On the scale of the cosmic calendar, recognizable animals became prominent only in mid-December. Early dinosaurs appeared on the day after Christmas. Then, in a cosmic instant, the dinosaurs disappeared forever, probably because of the impact of an asteroid or a comet. In real time, the death of the dinosaurs occurred some 65 million years ago, but on the cosmic calendar, it was only yesterday. With the dinosaurs gone, furry mammals inherited Earth. Some 60 million years later, or around 9 p.m. on December 31st of the cosmic calendar, early hominids' human ancestors began to walk upright. The most astonishing thing about the cosmic calendar is that the entire history of human civilization falls into just the last half-minute. The ancient Egyptians built the pyramids about 11 seconds ago on this scale. About 1 second ago, Kepler and Galileo proved that Earth orbits the Sun, rather than vice versa. The average college student was born about 0.05 seconds ago, around 11:59:59.95 p.m. on the cosmic calendar. In cosmic time, the human species is the youngest, and a human lifetime is a fleeting moment. Like the scale of space, the fantastic scale of time carries important lessons about extraterrestrial life if it exists. For example, the fact that the universe is so much older than Earth means that there ought to be many worlds with plenty of time for life to arise and evolve. If those worlds have had biological histories similar to Earth's, they might have had civilizations millions or even billions of years ago. We'll explore this idea and its astonishing implications. The scale of time also holds sobering lessons for our own future. Species have come and gone in the months of the cosmic calendar during which life has flourished on Earth, and there's no special reason to think that our fate should be any different. Unless we learn enough about ourselves and our planet to find ways to survive the next cosmic year, we will end up as little more than a momentary blip in the universe's long history. How big is the universe? We've stated that billions of galaxies exist in the universe, but can we be more precise? In fact, when we think of the universe as the sum total of all matter and energy, we really have no idea how large it is. The universe could well be infinite, which contains an infinite number of galaxies. However, the universe's age limits the portion of the universe we can see, even with the most powerful telescopes imaginable. Looking at vast distances, we also look far back in time. Nearest large galaxy to our own, the Great Galaxy in Andromeda, also known as M31. It is located about 2.5 million light-years away, this galaxy, as it was about 2.5 million years ago, long before modern humans even existed. This might seem like a long time in the past, but it's unlikely that the Andromeda galaxy looks significantly different today. It is so large that it takes some 200 million years to rotate once. So, in 2 million years, it barely changes. At much greater distances, however, we begin to see back to when the entire universe was significantly younger than it is today. Consider, for example, a galaxy that is 1 billion light-years away. Its light has taken 1 billion years to reach us, which means we see it as it looked 1 billion years ago, when the universe was only 13 billion years old, rather than its current 14 billion years. Next, consider a galaxy that is 7 billion light-years away. We see this galaxy as it looked 7 billion years ago, which means we see it as it was when the universe was only half its current age. If we look at a galaxy 12 billion light-years away, we see it as 12 billion years ago when the universe was only 2 billion years old. In a 14 billion-year-old universe, we cannot possibly see anything more than 14 billion light-years away. If we wanted to look more than 14 billion light-years away, say to a distance of 15 billion light-years, we'd be trying to look to a time before the universe existed, when there's nothing to see. Thus, our observable universe, the portion of the entire universe that we can potentially observe, consists only of objects that lie within 14 billion light-years of Earth. The concept of the observable universe carries at least 2 significant philosophical implications that warrant careful consideration. First, the fact that we cannot observe anything more than 14 billion light-years away does not mean that nothing exists at such distances. In fact, we have good reason to think that the universe goes on far beyond 14 billion light-years, and some evidence suggests that it is infinite in extent. We have no hope of seeing or studying any objects that lie beyond the bounds of our observable universe. Second, note that, by definition, we are at the center of our observable universe, as it has a defined light travel distance in all directions from us. However, being in the center of the observable universe is very different from being in the center of the universe. The latter would imply a special location, and the former does not. Observers on any planet, around any star in any galaxy, must also be at the center of their own observable universe. For example, people living in a distant galaxy would say the observable universe extends 14 billion light-years in all directions from them, rather than from us. You may realize that they can see at least some galaxies that we cannot, and vice versa, using their observable universe that overlaps ours. Thus, while the idea that we lie at the center of our observable universe may sound like a throwback to pre-Copernican times, it's not, since it still does not give us any special place in the universe. Worlds beyond imagination. Because the observable universe has a finite size, it must contain a finite number of galaxies. Unfortunately, there are too many to count, and some galaxies are too faint to see even with our best telescopes. Nevertheless, we can estimate the number of galaxies in the observable universe by counting the number we can see in pictures made with our most powerful telescopes. Photography by the Hubble Space Telescope, which shows a tiny piece of the sky in incredible detail. To understand what you see in this photo, imagine holding a grain of sand at arm's length against the sky. Everything you see would fit within the field of view directly behind that grain of sand. Almost every blob and dot in the photo is an entire galaxy of stars. Even the nearest of these galaxies are millions of light-years away, and the most distant ones, some of the tiniest dots, are more than 12 billion light-years away. Astronomers estimate that the observable universe contains about 100 billion galaxies by counting them and multiplying by the number of such photos it would take to make a montage of the entire sky. Like counting the Milky Way's 100 billion stars, counting all the visible galaxies would take thousands of years. Now let's think about the total number of stars in all these galaxies. If we assume 100 billion stars per galaxy, it would be similar to the Milky Way. How big is this number? Visit a beach. Run your hands through the fine-grained sand. Imagine counting each tiny grain of sand as it slips through your fingers. Then, imagine counting every grain of sand on the beach and continuing to count every dry grain of sand on Earth. On Earth. If you could complete this task, you would find that, roughly speaking, the number of grains of sand is comparable to the number of stars in the observable universe. The total number of worlds may be even greater, meaning any reasonably large bodies in space, such as planets, moons, or large asteroids. If planetary systems are as common as recent discoveries suggest, most stars have at least a few planets or moons. Clearly, our universe contains worlds beyond imagination. The incredible size of the universe poses a practical challenge to the search for life beyond Earth. We can no more hope to search all the possible places where we might find life than we could hope to study every grain of dry sand on every beach or Earth. Therefore, we will connect our discussions about the search for life to the search within the Milky Way galaxy, and assume that we would find similar results if we could study other galaxies. The fine-tuned universe. We have thoroughly reviewed the current state of our understanding of the universe and briefly discussed the evidence that has led us to this conclusion. But why is the universe like this? This may seem a strange question in a science book, but it is one that many scientists are now asking themselves. The interest in this question has been sparked by the realization that our universe appears to be fine-tuned for life. The logic behind the fine-tuning idea, sometimes known as the anthropic principle, goes like this. We are here today, able to study the universe and learn about its basic properties. But if any of those properties were much different, we could never have come to exist in the first place. For example, consider the expansion of the universe. If the universe were expanding rapidly, all its matter would have flown apart before gravity could have collected it into galaxies, stars, or planets. If the universe were expanding much more slowly, gravity would have pulled all the matter back together, causing the universe to collapse before there was time for life to get started. The expansion rate had to be just right for galaxies to form, which is even more remarkable when considering that the expansion needed to accelerate neither too much nor too little by now. There are similar things to think about when looking at many other basic properties of the universe, such as the relationship between the strengths of different forces, like gravity and the electromagnetic force, the size scale at which quantum effects become important, and even the fact that we live in 3 dimensions of space. Current theories of physics say that there are many more dimensions, so 3 wasn't the only option. In every case, a change, perhaps even a tiny one, could have prevented us from being here. There's no doubt that the universe really is fine-tuned in a way that makes our existence possible. The debate is over what this means. Some people argue that it is merely a philosophical question, since we obviously would not be here talking about it if it weren't so, in which case it falls outside the realm of science. Others argue that it implies some specialness to humans in particular, with a few going as far as to claim that we should conclude that we are unique, and hence the only life in the universe. Many physicists are searching for a natural explanation for the observed double M. Physicists are actively seeking a natural explanation for the observed fine-tuning. Physicists are actively seeking a natural explanation for the observed fine-tuning. One set of models that physicists have proposed to explain the workings of our universe suggests that, in fact, there should be a huge number of universes, sometimes called a multiverse. each with its own set of parameters, such as its number of dimensions, the ratio of force strength and expansion rate. In essence, this viewpoint holds that many universes exist, most of which are unsuitable for life. And we live in one of the rare universes that is suitable for life simply because we can. Other physicists believe that we will eventually discover a more straightforward explanation for why the universe turned out as it did. And once we do, we may realize that it had to be this way. As Einstein once stated, perhaps God had no choice in determining the parameters of creation. From this viewpoint, our apparent specialness may be a consequence of our still incomplete knowledge of physics, nature of worlds. Given that our galaxy contains far more worlds than we can study in detail, we can improve our odds of success in searching for life in the universe by constraining the search sensibly. One obvious way is to learn enough about planetary systems to make reasonable guesses as to which worlds are most likely to be habitable. In this section, we'll briefly survey how our current understanding of planetary science helps us understand the prospects of finding habitable worlds in our solar system and beyond. Before we begin, it's useful to have a clear picture of the solar system that you can refer back to as needed in the coming discussion. The solar system from beyond Neptune's orbit, so the planet's sizes are exaggerated to avoid appearing microscopic. As we observed earlier, the inner planets cluster much closer than the outer planets. Be aware that all planets orbit the Sun in the same plane, nearly circularly, and most rotate on their axes in the same direction. At the center of the solar system, the Sun rotates in the same direction that the planets orbit. And although it is not shown, a similar circumstance holds for most large moons, which orbit nearly in their planet's equatorial plane, and in the same direction that their planet, Earth. How do other worlds in our solar system compare to Earth? When people think of the ancient world, they typically envision a place similar to Earth, complete with a solid surface, oceans, and an atmosphere. In centuries past, many scientists also made this assumption. Even the moon was often thought to have enormous seas, or maria, Latin for seas, because the smooth, dark regions reminded 17th century scientists of the smooth surfaces of oceans, seen from afar. Only as telescopes improved and scientists developed techniques for determining the composition of distant worlds based on their light, did we learn that the moon is dry and barren. Today, no other planet in our solar system is as similar to Earth at its surface. No other world has surface oceans of liquid water, an atmosphere rich in oxygen, or a climate so hospitable to life. Nevertheless, planetary scientists have found that we can categorize worlds into groups by their general traits. Understanding these categorizations helps us understand the conditions that could make a world habitable. Let's look at the main categories that we will continue to discuss throughout this film series, which are based on the types of objects we find here in our own solar system. 2 major types of planets. The 8 planets in our solar system fall into 2 general groups by size. The 4 inner planets, Mercury, Venus, Earth, and Mars, are much smaller than the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. These size differences reflect basic differences in planetary character. The average densities of the 4 inner planets, composed almost entirely of metal and rock, are several times higher than those of water. They have solid surfaces, and their atmospheres, if any, are quite thin compared to the planets themselves. Because Earth is part of this group, we generally refer to these rocky worlds as terrestrial planets. Terrestrial means Earth-like. Note that the terrestrial planets have few moons. Earth is the only one with a large moon. Mercury and Venus have no moons. And Mars has 2 tiny moons. Jupiter, Saturn, Uranus, and Neptune are quite different in character and composition from the terrestrial planets. Because Jupiter is this group's largest member, we generally refer to these worlds as Jovian planets. Jovian means Jupiter-like. Rather than metal and rock, the Jovian planets are made largely of hydrogen, helium, and hydrogen compounds such as water, H2O, methane, CH4, and ammonia, NH3. Their composition gives them much lower average densities than the terrestrial planets. The Jovian planets of our solar system have at least 165 moons, with Jupiter alone having more than 60 known moons. All the Jovian planets have rings of countless small particles orbiting them, but only Saturn's bands are easily visible from Earth. This highlights the key differences between terrestrial and Jovian planets. Because hydrogen compounds are generally gases under earthly conditions, except for water, which can be solid, liquid, or gas, Earth's planets are often called gas giants. Due to high pressure in most of their interiors, these gases may be compressed into liquids or other high-density phases, causing them to behave differently than on Earth. More Earth. The Jovian planets' high pressure of the Jovian metal and rock deep in their cores makes them unlikely to resemble the solid surfaces of the terrestrial worlds. There would be no place to land on the Jovian planet if you dove into one of them. The mounting pressure would continue to crush you. Even within these two groups, planets differ greatly, and planetary research seeks to understand why those differences exist. For example, while all the terrestrial worlds have a similar overall composition, their surfaces look quite different. Among the Jovians, Uranus and Neptune contain much higher proportions of metal, rock, and hydrogen compounds than Jupiter and Saturn, which are mostly made from hydrogen and helium. Nevertheless, the importance of the general distinction between terrestrial and Jovian planets should be clear. If we assume that life needs a solid surface or oceans in which to get started, the Jovian planets seem far less likely to be habitable. Asteroids, comets, and dwarf planets. The 8 planets are the largest objects orbiting the Sun, but are not the only ones. Pluto, Eris, and other objects large enough for their own gravity to have made them round are now considered dwarf planets. The rest of the small bodies have traditionally been categorized into 2 groups: asteroids, made mostly of metal, and rock rockets, made mostly of rock and ice. There's little debate over the definition of an asteroid, an object that resembles a terrestrial planet in composition but is too small to count as a planet itself. Most asteroids orbit in the region called the asteroid belt, which lies between the orbits of Mars and Jupiter. However, the definition of a comet has been almost as contentious as the definition of a planet. Comets got their name, which comes from the Greek word for hair, from the objects with long tails that occasionally appear in our skies here on Earth. We now know that comets come from the distant reaches of the solar system, and they grow tails only when they come close enough to the Sun for the Sun's heat to convert some of their ice into gas. To determine where comets come from, astronomers have looked at their orbits and tracked how many we see in the inner solar system at any given time. They have found 2 large reservoirs. The Kuiper belt, Kuiper rhymes with Piper, which is beyond Neptune and contains Pluto, Eris, and many other similar but smaller objects, and the Oort cloud. Oort rhymes with court. Because the objects we see as comets in our sky must be only a tiny fraction of the similar objects in the Kuiper belt and Oort cloud, we've generally called these objects comets as well. The statistics tell us there must be millions of small comets in the Kuiper belt and as many as 1 trillion in the Oort cloud. Note that in location and composition, there is no doubt that both Pluto and Eris are members of the Kuiper belt, along with many other moderately large objects. In that sense, these objects are just unusually large comets, since they have the same general composition as much smaller comets that occasionally fall inward from the Kuiper belt toward the Sun. However, because of their large sizes, many astronomers are uncomfortable referring to Pluto and its cousins as comets and prefer the general term Kuiper belt objects, adding that they are dwarf planets that are round, moons. While moons are typically considered objects that orbit planets, Asteroids and cosmic objects can also have their own small moons. Pluto, for example, is orbited by 3 moons: Charon, about half the diameter of Pluto itself, and 2 smaller moons, Nix and Hydra, discovered in 2005. Most moons are small and considered asteroids or comets if they orbit the Sun independently. But a few moons are planet-like in size. Jupiter's moon, Ganymede, and Saturn's moon, Titan, are larger than the planet Mercury. And 4 other moons in our solar system, Jupiter's satellites, Io, Europa and Callisto, and Neptune's moon, Triton, are larger than Pluto. These and other relatively large moons are planet-like in almost every way except for their orbits. Some even have active geology or atmospheres. For example, Io is the most volcanically active world in our solar system. Europa must occasionally have water or ice flowing across its surface, and Titan has an atmosphere thicker than Earth's. The composition of the Earthoons varies according to their positions in the solar system. Our moon is made mostly of rock, much like the rocky composition of the terrestrial planets, though with some important differences too. Section 4.6. In contrast, the moons of the Jovian planets generally contain large amounts of ice, including water ice, H2O. When H2O combine this icy composition with the fact that some of the large Jovian moons have internal heat and geological activity, and you can see why scientists suspect some of them may hide oceans beneath their icy surfaces. Worlds come in different types. Knowing the different types of worlds in our solar system helps us understand their prospects of habitability. But we can gain even further insight by asking why worlds come in these different types. To answer this question, we must investigate the origin of our solar system, which in turn will give us insight into the prospects of finding habitable worlds in other star systems. Our current theory of the solar system's formation developed gradually over many decades, and like any theory, is still subject to modification. Section 3.5 will discuss some of this history and ongoing debate. Here, we will outline the basic features of this nebula theory, so named because it starts with the idea that our solar system was born from the gravitational collapse of an interstellar cloud, or nebula, of gas and dust. Nebula is Latin for cloud. The cloud that gave birth to our solar system is usually called the solar nebula. The solar nebula presumably began as a large, diffuse cloud, roughly spherical. We do not know precisely what caused this cloud to collapse under its own gravity, though some evidence points to a nearby supernova as the trigger. But observations of similar clouds that exist today show that they can indeed collapse and give birth to stars. Once the collapse began, the laws of physics ensured that the solar nebula would heat up, spin faster, and flatten into a disk as it shrank in size. The heating occurred because gas particles tend to move faster as they fall inward under gravity, much like a falling brick speeds up as it approaches the ground. The particles in the solar nebula collided with each other as they fell inward, transforming their motion energy into heat. The cloud became hottest near the center where the sun formed. In more technical terms, this heating resulted from the law of energy conservation. This law states that energy can be neither created nor destroyed, but only transformed from one form to another. The cloud began with a tremendous deal of gravitational potential energy. Energy it had because its particles were far from the cloud's center, and this energy was transformed into heat. The cloud's spin resulted from another physical law known as the conservation of angular momentum. This law essentially states that an object's total amount of circling motion, or set of objects, must be conserved. We won't go into the details here, but you've probably seen this law in action with ice skating. It explains why a spinning skater's rate of spin increases when she pulls in her arms. In much the same way, a shrinking gas cloud must spin faster as it contracts, as long as it has at least some small spin rate. In the case of interstellar clouds, random motions ensure that they almost inevitably have some small overall rotation, though it is often imperceptible when the cloud is large. As the cloud shrinks, its spin becomes noticeable and fast. The flattening was a consequence of the spin. Particles colliding in a spinning cloud add to each other's motion in the rotation direction, but cancel each other out in other directions. Much like a spinning ball of pizza dough, this tends to force all the particles to end up in a flattened spinning disk. Observations show that many young stars are surrounded by such flattened spinning disks of material, just as we should expect from the nebula theory. Gravity gathered enough material in the disk's center to form the Sun. In the surrounding disk, the gaseous material was too spread out for gravity alone to clump it up. Instead, the material had to begin clumping some other way and grow in size until gravity could pull it together into planets. In essence, planet formation required the presence of seeds, solid bits of matter around which gravity could ultimately build planets. The basic process of seed formation was probably much like the formation of snowflakes in clouds on Earth. When the temperature is low enough, some atoms or molecules in a gas may bond together and solidify. The general process in which solid or liquid particles form in a gas is called condensation. We say that the particles condense out of the gas. Different materials condense at different temperatures. Since hydrogen and helium gas comprised 98% of the solar nebula's mass and did not condense, most of the nebula remained gaseous. However, other materials could condense wherever the temperature allowed. Only rock and metal can condense in the inner solar system, where temperatures are high, while hydrogen compounds are primarily gaseous. Farther out, where temperatures were much lower, hydrogen compounds could condense to make solid bits of ice. The first particles to condense were microscopic and orbited the Sun with the same orderly circular paths as the gas from which they condensed. Individual particles moved at nearly the same speed as their neighboring particles, resulting in collisions that resembled gentle touches. Under these circumstances, particles could stick together through electrostatic forces, the same static electricity that makes hair stick to a comb. Small particles thereby began to combine into larger ones. Once the particles grew to sizes of a kilometer or more, gravity began to aid the process of their sticking together, accelerating their growth. Two types of planets. We can use the processes of condensation and accretion to explain why the solar system ended up with two types of planets. Only metal and rock could condense into solid particles in the inner solar system, forming the planetesimals. These planetesimals grew rapidly at first, with some probably reaching hundreds of kilometers in size in only a few million years. A long time in human terms, but only about 1,000th the present age of the solar system. Further growth became more difficult once the planetesimals reached these relatively large sizes. Gravitational encounters between planetesimals tended to alter their orbits, particularly those of smaller planets. With different orbits crossing each other, collisions between planetesimals occurred at higher speeds, becoming more destructive. Such collisions produced fragmentation more often than accretion. Only the largest planetesimals escaped fragmentation and developed into full-fledged terrestrial planets. The planet formation process probably began similarly in the outer solar system, except the lower temperatures meant that ice condensed along with metal and rock. Because ice was more abundant than rock and metal, icy planetesimals grew larger in the outer solar system than the rocky planetesimals of the inner solar system. According to the leading model of Jovian planet formation, some of the icy planetesimals grew to masses many times that of Earth. With these large masses, their gravity became strong enough to capture and hold on to some of the hydrogen and helium gas that comprised most of the surrounding solar nebula. As the growing planets accumulated gas, their gravity grew stronger. allowing them to capture even more gas. Ultimately, the Jovianettes grew so much that they bore little resemblance to the icy seeds from which they started. Moons. This model also explains why Jovian planets tend to have many moons. The same heating, spinning, and flattening processes that made the solar nebula disk should have also affected the gas drawn by gravity to the young Jovian planets. A disk of gas surrounded each Jovian planet, spinning in the same direction as the planet's rotation. Moons could accrete from icy planetesimals within these disks, which probably explains the formation of most of the large moons of the Jovian planets. Asteroids or comets likely captured the smaller moons. Because objects can be captured only if they are slowed enough to enter an orbit around a planet, models predict that nearly all of the captures would have happened early in the solar system's history, when the Jovian planets were still surrounded by disks of gas that could exert friction to slow down passing asteroids or comets. The general lack of moons among the terrestrial planets also makes sense. Captures were far less likely since the terrestrial planets were not surrounded by large disks of gas, and there was no place for large moons to accrete. Of course, this raises the question of how to account for the existence of an exceptionally large moon. As previously discussed, the leading hypothesis for the formation of our moon suggests a massive collision between Earth and other large planetesimals, which must have roamed the solar system early in its history. Asteroids and comets. The nebula theory likely explains the existence of numerous asteroids and comets. They are leftover planetesimals from the era of planet formation. Asteroids are the leftover rocky planets of the inner solar system, while comets are the leftover icy planets of the outer solar system. Asteroids tend to reside in the asteroid belt because the influence of Jupiter's gravity herds them in a way that makes them less likely to suffer collisions than asteroids in other solar system regions. Therefore, while most asteroids in other regions of the inner solar system long ago crashed into one of the planets, asteroids of the asteroid belt had a decent chance of surviving to the present day. Scientists believe they understand the division of comets into two regions, the Kuiper belt and the Oort cloud. The Kuiper belt comets probably reside in the same general region they formed. This region, which lies beyond the orbit of Neptune, was relatively low in density. So while none of the planetesimals grew large enough to become a fifth Jovian planet, some grew to the size of Pluto and Eris, making them examples of what we now call dwarf planets. While hundreds of thousands of smaller comets also survive to the present day. The Oort cloud comets are now thought to have originated in regions where they crossed the orbits of the Jovian planets. When one of these comets passed near a Jovian, it was likely to be flung out to a considerable distance by the planet's gravity, much like scientists have taken advantage of Jupiter's gravity to accelerate spacecraft to planets. While it may sound strange for gravity to fling an object away, it's a direct consequence of the law of energy conservation. When two objects interact through their gravity, their combined energy must remain unchanged, which means that one will lose power and the other will gain it. For Jupiter and a comet, Jupiter's loss or gain of energy would be unnoticeable, because it is so much larger, while the comet's gain, or loss, would completely change its orbit. One key question remains for us to answer. Given that the vast majority of the hydrogen and helium gas in the solar nebula never became part of any planet, what happened to it? Models and observations of other star systems suggest that it was cleared away by a combination of energetic light from the young sun and the solar wind, a stream of charged particles continually blown outward in all directions from the sun. The solar wind was almost certainly much stronger when the sun was young than today. Once the gas cleared, it sealed the planet's compositional fate. If the gas had remained longer, it might have continued to cool until hydrogen compounds condensed into ice, even in the inner solar system. In that case, the terrestrial planets may have accreted abundant ice and some hydrogen and helium gas, changing their basic nature. In contrast, if the gas had been blown out earlier, the planet's raw materials may have been swept away before they could form. Although these extreme scenarios did not occur in our solar system, they may sometimes occur around other stars. As discussed, both theory and observation support that most stars are born surrounded by gas and dust spinning disks. Once a disk forms, we expect condensation, much like in the solar system, with metal and rock particles in the hot inner regions and ice particles in the cold outer regions. Thus, based only on what we see in our solar system, we expect to find many other planetary systems with terrestrial and Jovian planets laid out in the same general way as in our solar system. Therefore, we might expect habitable terrestrial planets and Jovian moons to be common throughout the galaxy. Before the discoveries of extrasolar planets, astronomers assumed this would be the case, with most other planetary systems laid out much like ours. However, as we'll discuss further in Chapter 11, the reality appears more complex. Many other planetary systems so far discovered have planets with unexpected orbits, such as Jovian planets orbiting close to their stars. We don't yet know if planetary systems like ours are the norm or the exception, as these systems are also easier to discover than ours. At this point, we cannot confirm whether habitable planets are rare or common due to uncertainty. Nevertheless, given the vast number of stars in the Milky Way galaxy, even rare could mean large total numbers. For example, if only 1 in a million other star systems is like ours, that would still mean some 100,000 such systems among 100 billion stars. Because 100 billion, 1 million, 100,000. Unless there is a significant discrepancy in our understanding of planet formation, it appears highly likely that our galaxy harbors numerous worlds with liquid water, making them ideal habitats for life. We have now surveyed modern understanding of the universe on a large scale and considered how this understanding affects the possibilities for extraterrestrial life. The small-scale universe is equally important, because life, like everything else in the universe, is, at its most basic level, an interplay of the things that we call matter and energy. We have already talked a fair amount about matter and energy in passing, as it's hard to discuss science without these concepts. However, for our purposes in this book, you need to be familiar with more details related to matter and energy as we understand them today. Unless you already know these details, this section should give you the background you need for the rest of the book. Note that we will restrict our focus to ordinary matter and energy, ignoring the dark matter and dark energy that may make up most of the content of the universe. Although this may seem a rather large restriction, the ordinary matter and energy appear to be all we need to understand stars, planets, and life. We discussed the ancient Greek idea that matter consists of 4 elements: fire, water, and earthly air, and the further assumption of some philosophers that these elements come in tiny indivisible pieces that they called atoms, a Greek term meaning indivisible. The idea is similar today, but there are many more elements besides fire, water, earth, and air. In addition, we now know that the atoms that make the elements are made from smaller pieces. Let's briefly look at our current understanding of atoms and other microscopic forms of matter. Atomic structure. Atoms come in different types, and each type corresponds to a different chemical element. The most familiar chemical elements are hydrogen, helium, carbon, oxygen, silicon, iron, gold, silver, lead, and uranium. Atoms are made of particles called protons, neutrons, and electrons. Protons and neutrons are found in the tiny nucleus at the center of the atom. The rest of the atom's volume contains electrons that surround the nucleus. Although we can think of electrons as tiny particles, they are not quite like tiny grains of sand. They don't orbit the nucleus like planets orbit the sun. Instead, the electrons in an atom form a kind of smeared-out cloud that surrounds the nucleus and gives the atom its apparent size. The electrons aren't really cloudy, but it is impossible to pinpoint their positions in the atom. First, notice that atoms are incredibly small. The number of atoms in a single drop of water, typically 10 atoms, may equal the number of stars in the observable universe. At the same time, the electrons give the atom a size far larger than its nucleus. If you imagine an atom on a scale whose nucleus is the size of your fist, its electron cloud would be many kilometers wide. Nevertheless, most of the atom's mass resides in its nucleus, because protons and neutrons are each about 2,000 times as massive as an electron. The properties of an atom depend mainly on the amount of electrical charge in its nucleus. An object's electrical charge is a measure of how strongly it will interact with other charged particles. We define the electrical charge of a proton as the basic unit of positive charge, which we write as +1. The electron has an electrical charge that is precisely opposite to a proton, so we say it has a negative charge -1. Neutrons are electrically neutral, meaning that they have no charge. Oppositely charged particles attract one another, and similarly charged particles repel one another. An atom is held together by the attraction between the positively charged. Most atoms in and around you contain the same number of electrons as protons, making them electrically neutral overall. However, atoms often lose or gain electrons, in which case they obtain a net electrical charge. We call such atoms ions. A positive ion is an atom that has lost one or more electrons, so that it has more positive than negative charge overall. A negative ion is an atom that has gained one or more electrons, giving it a net negative charge. The net electrical charge of an atom turns out to be exceedingly important to life. The deep burying of the nucleus within an atom almost exclusively leads to interactions between electrons. Indeed, these electrical interactions between atoms essentially make up everything that we think of as chemistry. And since chemical reactions are the foundation of all the processes that occur in living organisms, we see that the electrical interactions of atoms underlie everything we know about life. We will use several pieces of atomic terminology throughout this film. First, each chemical element contains a different number of protons in its nucleus, which is its atomic number. For example, a hydrogen nucleus contains just one proton, so its atomic number is 1. A helium nucleus contains 2 protons, so its atomic number is 2. The complete set of more than 100 known elements is listed in the periodic table. An atom's combined number of protons and neutrons is called its atomic mass number. The atomic mass number of ordinary hydrogen is 1 because its nucleus is just a single proton. Helium usually has 2 neutrons and 2 protons, giving it an atomic mass of 4. Carbon usually has 6 protons and 6 neutrons, giving it an atomic mass number of 12. Every atom of a given element contains the same number of protons, but the number of neutrons can vary. For example, all carbon atoms have 6 protons, but may have 6, 7, or 8 neutrons. Versions of an element with different numbers of neutrons are called isotopes of the element. Isotopes are named by listing their element name and atomic mass number. For example, the most common carbon isotope has 6 protons and 6 neutrons, giving it atomic mass. Number 6 plus 6 equals 12, so we call it carbon-12. The other isotopes of carbon are carbon-13. 6 protons and 7 neutrons give it atomic mass number 13. And carbon-14, 6 protons and 8 neutrons give it atomic mass number 14. We can also write the atomic mass number of an isotope as a superscript to the left of the element symbol. 12C, 13C, 14C. We read 12C as carbon-12. The number of different material substances is far greater than chemical elements because atoms can combine to form molecules. Some molecules consist of 2 or more atoms of the same element. For example, we breathe O2, oxygen molecules made up of 2 oxygen atoms. Other molecules, such as water, are atoms of 2 or more elements. The symbol H2O tells us that a water molecule contains 2 hydrogen and 1 oxygen atom. Compounds are substances composed of molecules with 2 or more different types of atoms. Thus, water is a compound. The chemical properties of a molecule are different from those of its individual atoms. For example, molecular oxygen, O2, behaves differently from atomic oxygen, O, and water behaves differently from pure hydrogen or pure oxygen. Life on Earth is based on the complex chemistry of molecules, compounds, containing carbon, which are called organic molecules or organic compounds. Diagrams often depict molecules using ball and stick models, which illustrate the arrangement of their atoms. Everyday experience tells us that a substance can behave dramatically differently in different phases, even though it is still made of the same atoms or molecules. For example, molecules of H2O can exist in 3 familiar phases: as solid ice, as liquid water, and as the gas we call water vapor. How can the same molecules look and act differently in these different phases? You are probably familiar with the idea of a chemical bond, the name we give to the interactions between electrons that hold the atoms in a molecule together. For example, we say that chemical bonds hold the hydrogen and oxygen atoms together in a molecule of H2O. Similar but much weaker interactions among electrons hold together the many water molecules in a block of ice or a pool of water. We can think of the interactions that keep neighboring atoms or molecules close together as another type of bond. If we think of bonds, the phases of solid, liquid, and gas differ in the strength of the bonds between neighboring atoms and molecules. Phase changes occur when one type of bond is broken and replaced by another. Changes in either pressure or temperature, or both, can cause phase changes. But it's easier to think about temperature. Consider water as an example. Figure 3.26. At low temperatures, water molecules tightly bind to their neighbors, forming the solid structure of ice. As long as the temperature remains below freezing, the water molecules in ice remain rigidly held together. We often say that they have a crystal structure, meaning that the molecules are arranged in a precise geometrical pattern. However, the molecules within this crystal structure always vibrate. Higher temperature means greater vibrations. The melting point, 0 degrees Celsius at sea level on Earth, is the temperature at which the water molecules finally break the solid bonds of ice. The molecules can then move much more freely among one another, allowing the water to flow as a liquid. That water droplets stay intact shows that liquid water molecules are not completely free of each other. Thus, adjacent molecules in liquid water are still held together by a type of bond, though it is much looser than the one that holds them together in solid ice. If we continue to heat the water, the average speeds of the water molecules increase, and high enough speeds will ultimately break the bonds between neighboring molecules altogether. The molecules will then be able to move freely, and free-moving particles constitute what we call a gas. Above the boiling point, 100 degrees Celsius at sea level, all the bonds between adjacent molecules are broken so that the water can exist only as a gas. We frequently witness the transformation of ice into liquid water and liquid water into gas, leading us to believe that this is the conclusion of the story. However, a little thought should convince you that the reality has to be more complex. For example, you know that Earth's atmosphere contains water vapor that condenses to form clouds and rain. However, given that Earth's temperature is significantly lower than the boiling point of water, how is it possible for our atmosphere to hold water in its gaseous state? You'll understand the answer if you remember that temperature measures the average motion of the particles in a substance. Individual particles may move substantially faster or slower than the average. Even at the low temperatures at which most water molecules are bound together as ice or liquid, a few molecules will always move fast enough to break free of their neighbors, and enter the gas phase. In other words, some gas, water vapor, is always present along with solid ice or liquid water. The process by which molecules escape from a solid is called sublimation, and the process by which particles escape from a liquid is called evaporation. Higher temperatures lead to higher rates of sublimation or evaporation. The same basic ideas hold true for other substances, but their melting and boiling temperatures differ from water's. Moreover, although we won't go into detail here, remember that pressure also has an important effect. For example, high pressure can cause a substance to remain in the solid phase even when the temperature is above the low-pressure boiling point. At the beginning of this film, we stated that life, like everything else in the universe, is an interplay between matter and energy at its most basic level. We've briefly discussed the makeup of matter. But what is energy? In essence, energy is what makes matter move. Because this statement is so broad, we often distinguish among many different types of energy. For example, we talk about the energy we get from the food we eat, the energy that makes our cars go, and the energy a light bulb emits. Fortunately, we can classify all these various types of energy into just three major categories. Kinetic energy, derived from the Greek word meaning motion, is the energy of motion. Falling rocks, orbiting planets, and the molecules moving in the air around us are all examples of objects with kinetic energy. Energy carried by light, or radiative energy, the word radiation, is often used as a synonym for light. All light carries energy, which is why it can cause changes in matter. For example, light can alter molecules in our eyes, thereby allowing us to see, or warm the surface of a planet. Later, we can convert stored or potential energy into kinetic or radiative energy. For example, a rock perched on a ledge has gravitational potential energy because it will fall if it slips off the edge, and gasoline contains chemical potential energy that can be converted into the kinetic energy of the moving car. Einstein discovered that mass itself is a form of stored energy, sometimes called mass energy, as described by his famous formula E equals mc squared, introduced earlier in the chapter. Energy can change from one form to another. Indeed, such changes are the primary drivers of life. For example, our bodies take the chemical potential energy stored in food and use it to make molecules move, allowing our leg muscles to contract for walking, our blood and skin to create scabs over wounds, and neurons in our brains to fire in ways that make thought possible. However, while energy can change from one form to another, it can be neither created nor destroyed. This idea, which we discussed briefly earlier, is the law of energy conservation. This law helps us understand everything from how the sun and planets formed, discussed earlier, to the requirements of life. Although some form of stored energy is available almost everywhere, in most cases, there is no viable way for life to extract it for its own use. As we'll discuss in later chapters, the availability of a viable energy source is one of the crucial factors determining a world's habitability. What is light? Our information about distant planets and stars comes from studying their light. Let's briefly examine key properties of light that allow us to learn so much from it. As we have already seen, light is a form of energy that travels through space at the high speed of 300,000 kilometers per second. More specifically, light is characterized by rapidly changing electric and magnetic fields, so we often call light an electromagnetic wave, figure 3.28. Like other types of waves, such as water waves, sound waves, or waves on a vibrating string, light is characterized by a wavelength, the distance between adjacent peaks of the electric or magnetic field, and a frequency, the rate at which the electric and magnetic fields change. The standard unit of frequency, hertz, is equivalent to waves per second. For example, 103 Hz means that 103 wave peaks pass by a point each second. Unlike most other types of waves, light also exhibits properties that we usually attribute to particles. In particular, light comes in distinct pieces, called photons, that can exert pressure, knock electrons out of atoms, or cause molecules to rotate and vibrate. In other words, light is both a wave and a particle. So the best way to think of it is as a collection of photons characterized by wavelength and frequency. A simple formula relates the wavelength and frequency of a photon. At the same speed, we find that longer wavelength means lower frequency, and shorter wavelength means higher frequency. The energy of a photon is proportional to its frequency, so a higher frequency of light has higher energy. Light can have any wavelength, frequency, or energy. The complete range of possibilities is called the electromagnetic spectrum. For convenience, we refer to different portions of the electromagnetic spectrum by name. The visible light we see with our eyes is only a tiny portion of the complete spectrum, with wavelengths from about 400 nanometers at the blue end of the rainbow to about 700 nanometers at the red end. 1 nanometer, nm, is a billionth of a meter. We refer to light with wavelengths slightly longer than red as infrared because radio waves are the longest wavelength light. Be sure to note that radio waves are a form of light, not sound. The region near the border between infrared and radio waves, representing wavelengths from micrometers to centimeters, is sometimes named microwaves. On the other side of the spectrum, light with wavelengths somewhat shorter than blue light is called ultraviolet, because it lies beyond the blue, or violet, end of the rainbow. Light with even shorter wavelengths is called X-rays, and the shortest wavelength light is called gamma rays. Notice that visible light is an insignificant part of the entire electromagnetic spectrum. The reddest red that our eyes can see has only about twice the wavelength of the bluest blue. But the radio waves from your favorite FM radio station are 1 billion times longer than the X-rays used in a doctor's office. The different energies of different forms of light explain many familiar effects in everyday life. Radio waves carry so little energy that they have no noticeable effect on our bodies. However, radio waves can make electrons move up and down in an antenna, which is how the antenna of your car radio receives the radio waves coming from a radio station. Molecules moving around in a warm object emit infrared light, which is why we sometimes associate it with heat. Receptors in our eyes respond to visible light photons, making vision possible. Ultraviolet photons carry enough energy to harm cells in our skin, causing sunburn or skin cancer. X-ray photons have enough energy to penetrate skin and muscle, but can be blocked by bones or teeth. That is why doctors and dentists can see our underlying bone structures in photographs taken with X-ray light. Learning from light. The most obvious way to learn about a distant object from its light is to use a telescope to photograph it. But there are also other ways to learn from light. For our purposes in this book, one particular way of learning from light is especially important. Spectroscopy, which involves collecting light through a telescope and then dispersing it into a spectrum in much the same way a prism disperses white light into a rainbow of color. The 3 basic types of spectra that we observe are: 1. A continuous spectrum contains smooth light across a broad range of wavelengths. 2. An emission line spectrum has bright lines on a dark background. And 3. An absorption line spectrum has dark lines on a continuous background. Like a light bulb, a hot object produces a continuous spectrum. In fact, any dense object emits continuous light, characteristic of the object's surface temperature and often called thermal radiation. The thermal radiation spectrum varies depending on the temperature of the object. Notice that a star like the Sun emits more strongly invisible light than at any other wavelength, while a typical planet emits infrared light but no visible light at all. This fact allows us to learn a distant object's temperature just by measuring where its thermal radiation spectrum peaks. Moreover, we can learn even more about objects like planets that reflect sunlight by studying which wavelengths of light are reflected most strongly. For example, Mars not only emits its own infrared light, from which we learn its temperature, but also reflects visible light from the Sun. Mars reflects red light more strongly than blue light, hence its red color, helping us identify minerals and ice on its surface. Spectral lines can provide even more information. Every chemical element, every ion of each element, and every molecule produces its unique pattern of spectral lines. In essence, this pattern represents a chemical fingerprint that allows us to identify what produced it. By carefully studying a spectrum, we can determine the chemical composition of distant objects. That is how we learn the chemical compositions of stars, gas clouds, and planetary atmospheres. Different isotopes of an element also have slightly different spectra, so we can sometimes even determine isotopic ratios in distant worlds. By studying spectral lines in detail, for example, how bright or dark they are, how wide they are, and what precise set of atoms and ions is represented in a spectrum, scientists can infer even more information about distant objects. Perhaps most importantly, the Doppler effect causes the precise positions of spectral lines to shift with an object's motion relative to us. We can use this effect to determine the speed of any distant object, which has allowed us to discover and measure the masses of many planets around other stars. In addition, careful study of spectral lines can sometimes tell us such things as an object's temperature, rotation rate, pressure, density, and magnetic field strength. Today, we are confident that our solar system was born from the gravitational collapse of an interstellar cloud. But how did scientists accept this idea? And why are we so confident that it is correct? Scientific progress generally involves proposing a model to explain various observations and then testing that model. More than one model may often be proposed, and the competition among models helps us develop them further until one clearly wins out over the others. The development of our current model of the solar system's formation, which we now consider a theory because its evidence is so strong, occurred precisely this way. Moreover, as is always the case with scientific theories, the nebula theory is subject to ongoing debate and modification. Because the nebula theory is critically important to studying life in the universe. After all, it explains how a planet like ours came to exist. We will use its history and ongoing development as this chapter's case study in the process of science in action. How did the nebula model win out over competing models? After the Copernican revolution, Earth was established as just one planet in our solar system, and it was only natural that scientists began to speculate about how our solar system came to be. Around 1755, German philosopher Immanuel Kant proposed that our solar system formed from the gravitational collapse of an interstellar gas cloud. About 40 years later, French mathematician Pierre-Simon Laplace put forth the same idea independently, apparently unaware of Kant's proposal. Because an interstellar cloud is usually called a nebula, the idea of Kant and Laplace became known as the nebula hypothesis. The Kant/Laplace nebula hypothesis may sound quite similar to our nebula theory today, but there was an important difference. While we now have a detailed model and plenty of evidence to support the modern theory, there was little evidence at the time to support the Kant/Laplace hypothesis. Other scientists, therefore, put forth other ideas. For example, in 1745, or 10 years before Kant's publication, French scientist Georges Buffon suggested that the planets had been born when a massive object, which he guessed to be a comet, collided with the Sun and splashed out debris that coalesced into the planets. This basic idea became the leading competitor to the nebula hypothesis. It took almost 200 years for science to collect enough data to allow us to choose between these two general ideas about how our solar system was born. To understand how one model won out, we must first understand a bit more about how we decide what types of observations a theory must explain. The primary goal of a scientific theory is to explain a broad range of diverse observations in terms of just a few fundamental principles. But what observations should we focus on? You might at least guess that we'd want a theory to be able to explain everything about a particular topic. But that is neither realistic nor even useful. For example, while we expect any theory of gravity, whether it is Newton's theory, Einstein's theory, or a future theory that is even broader, to explain planetary orbits and Galileo's discovery that mass does not affect an object's rate of fall, we do not expect the theory of gravity to explain why a sheet of paper falls more slowly when it is flat than when it is crumpled up into a small ball. The falling paper is certainly affected by gravity, but we recognize that it is also subject to other forces, such as air resistance, and we don't expect gravity alone to explain the paper's motion. To come up with a good theory of gravity, it was important to understand the differences between observations that gravity alone should be able to explain, and those that might also be affected by something else. In the case of the solar system, an enormous number of observations might seem at least potentially relevant, from general characteristics of planetary orbits to the shapes of individual asteroids. Historically, scientists have focused on different sets of observations at different times as we've learned more about the solar system. At the time of Buffon, Kant, and Laplace, before asteroids had been discovered, and before we recognized differences between terrestrial and Jovian worlds, the focus was almost entirely on explaining the mere existence of planets. Later, as astronomers began to realize that asteroids and comets are by far the most numerous of the bodies in the solar system, it became important for the theory to be able to explain their existence and their orbits, and fairly obvious that their general characteristics are much more essential than their individual shapes. Today, we expect a formation theory to explain our solar system and our observations of planets in other star systems. Overall, we can group the many known properties of our own solar system into a list of 4 major features that a theory of its formation must explain. The theory aims to explain the orderly motions of large bodies. The theory should explain the organized patterns we see in the orbits and rotations of the larger objects of our solar system. Recall, for example, that all the planets orbit the Sun with nearly circular orbits, all going in the same direction and plane. The orbital direction, counterclockwise as viewed from far above Earth's North Pole, is the same as the direction of the Sun's rotation, the direction of most planet rotations, and the direction in which most large moons orbit their planets. There are 2 types of planets. We must also explain why the planets divide clearly into 2 groups. The small rocky terrestrial planets are close together and close to the Sun, while the large gas-rich Jupiterian planets are farther apart and farther out. Small bodies. The planets are far outnumbered by small bodies. Asteroids, comets in both the Kuiper Belt and the Oort cloud, and Kuiper Belt objects. So we must also explain how these objects formed and came to be in their current orbits. There are notable exceptions to the rules. The generally orderly solar system also has some notable exceptions to the rules. For example, Earth is unique among the inner planets in having a large moon, and Uranus has an odd, sideways tilt. A successful theory of our solar system must make allowances for such exceptions, even as it explains the general rules. We have already seen how the nebula theory explains the first 3 features. The orderly motions result from how the Sun and planets were born in a spinning disk of gas. The 2 types of planets arose because different materials condensed and accreted at different distances from the Sun. Small bodies are essentially leftovers from the birth of the planets. We have not yet discussed the exceptions to the rules, but we suspect most of them result from collisions between some of the leftovers and the planets. The fact that so many small bodies still exist tells us that at least some large collisions must have been likely in the past. So this idea is fully consistent with the nebula theory. Given all this success, why did it take so long for the nebula theory to gain acceptance? The gradual collection and study of evidence is the answer. Although Buffon's idea of planets forming in a collision with the Sun always had some supporters, the Kant-Laplace nebula hypothesis was more popular in the 19th century. By the early 20th century, however, scientists had found a few aspects of our solar system that the nebula hypothesis did not seem to explain well, at least in its original form. In particular, Laplace had proposed a physical mechanism by which he claimed the planets were made. His mechanism envisioned the planets forming in successive rings of gas that formed as the cloud contracted and spun faster. But the details are unimportant here. Instead, an important point is that his mechanism was testable. And as scientists began to put it to the test, they found that it did not work. Laplace's mechanism could not actually build planets as he had thought. This failure meant the model needed to be either modified or discarded. Some scientists sought to modify the nebula hypothesis by looking for alternative ways to build planets, while others looked for entirely different ideas about how the solar system might have formed. Before too long, a new version of Buffon's old idea began to gain favor. In this new version, scientists imagined a near collision between the Sun and another star, instead of directly colliding with the Sun. According to this close encounter hypothesis, the planets form from blobs of gas that had been gravitationally pulled out of the Sun during the near collision. The two models engaged in a close battle for several decades. Each had features that agreed well with observations, and no conclusive evidence favored one. However, as scientists studied the models in greater depth, they learned to calculate the consequences of each one more precisely. By the middle of the 20th century, these calculations showed that the close encounter hypothesis could not explain how the planets were seen to move in their orbits, or how they could be neatly put into two groups, terrestrial and Jovian. With this clear failure, the close encounter model rapidly lost favor. Moreover, this failure made scientists take a second problem with the model more seriously. It required a highly improbable event. Given the vast separation between star systems in our region of the galaxy, the chance that any two stars would pass close enough to cause a substantial gravitational disruption is so small that it would be difficult to imagine it happening even in the one case needed to make our own solar system. While low probability alone could not rule out the close encounter hypothesis, it certainly did not help the case for a hypothesis that also failed on other grounds. Today, we can rule out the close encounter hypothesis definitively, because the low probability of forming planets in collisions leads to a testable prediction that we now know to be wrong. If planets are born only in rare events, then planets should be rare around other stars. The fact that we now know planets to be quite common rules out the close encounter hypothesis. At the same time that the close encounter hypothesis was losing favor, new ideas about the physics of planet formation led to modifications of the nebula hypothesis. Laplace's mechanism was discarded and replaced by the idea of condensation and accretion. And scientists soon realized that this important modification could allow the nebula model to explain the major features of our solar system. Perhaps even more important, new discoveries about our solar system, such as learning about the Kuiper belt and Oort cloud and the differing compositions of planets and moons, fit well into the nebula model. By the latter decades of the 20th century, so much evidence had accumulated in favor of the nebula hypothesis that it achieved the status of a scientific theory. The nebula theory of our solar system's birth. The historical competition between the nebula and close encounter models may sound like scientific trivia, but it profoundly affected attitudes about life in the universe. The reason is probably clear. If the close encounter hypothesis had been correct, other planetary systems would have been exceedingly rare. we probably wouldn't have found any other habitable planets in our galaxy or the universe. In that case, any chance of finding life beyond Earth would have been limited to the other worlds in our solar system. This model seemed quite plausible for much of the first half of the 20th century, and partially explains why scientific interest in extraterrestrial life waned during that period. Once the close encounter model was discarded and the nebula theory gained acceptance, it became clear that other planetary systems were to be expected, making the possibility of life in other worlds seem far more reasonable. Given the strength of evidence for the nebula theory, you might at first expect it to be considered settled science, with nothing left to learn about it. However, recalling our previous discussion on gravity, it is important to remember that even the most robust theories are subject to change. Just as physicists are engaged in the great debate over what theory of gravity will replace and improve on Einstein's, the nebula theory is one of the hottest debate topics in modern planetary science. New discoveries typically drive the scientific debate. The new discoveries force a reconsideration of the nebula theory in two major categories. First, there are the extrasolar planets with their surprising orbits. Second, increasingly powerful telescopes enable us to witness the phenomena accompanying stellar birth through new observations of young star systems. The two sets of new evidence are interrelated and must be considered simultaneously by scientists. But let's start by focusing on the implications of the extrasolar planet discoveries. As we've discussed, scientists developed the nebula model so that it neatly explains why Jovian planets in our solar system exist only far from the Sun, while the terrestrial planets exist only close in. The discovery of extrasolar planets that are massive like Jovian planets but located in their inner solar systems was therefore quite unexpected, and it immediately caused scientists to begin questioning the nebula model. Initially, a number of scientists questioned whether the nebula model was fundamentally flawed and required complete discarding. However, observations of star-forming clouds and young star systems have made scientists increasingly confident that stars and planets are born in collapsing clouds of gas. The issues with the nebula theory must have more to do with the details of what happens after the cloud forms a spinning disk around a young star. We still do not know exactly how to reconcile the surprising planetary orbits with the mechanism of planetary formation in the current nebula theory. But scientists have many plausible ideas. For example, one set of models that looks quite promising starts by assuming that Jovian planets do indeed form in their outer solar systems, but that gravitational interactions or other processes occurring in the spinning disk can cause them to migrate inward after they form. Scientists are trying to model this process with computer simulations to see whether it works or whether other ideas are needed to reconcile the nebula theory with observed extrasolar planets. Observations of young star systems have also revealed plenty of surprises. The basic model of the nebula theory makes the planetary formation process look rather smooth and calm, except in the late stages of accretion when shattering collisions become possible. However, observations of young stars show that their births are actually quite violent. Even as gas falls inward to make a central star and a rotating disk, we observe huge jets of matter being shot outward along the disk's rotation axis. Astronomers are working hard to understand exactly what causes these powerful outflows of matter, which proves that star formation is a much more complex process than the basic nebula model presumes. Other observations lead to a more detailed understanding of how the central star is born, a process that sheds further light on the formation of the surrounding disk. Observations of disks themselves also reveal surprises. Some relatively old stars still have disks, suggesting that planets may not be an inevitable outcome of star formation. Other disks show structure indicating that they are quite turbulent, which has led some scientists to explore the idea that Jovian planets might be born from instabilities in the disk, rather than from condensation and accretion. The overall point should be clear. The nebula theory explains the basic concept so well that it stands on solid ground. However, much remains to be learned about its details,